Welcome, everybody. This is a highly anticipated part of our program this weekend, as is all the other presentations. It's a little bit different because we're bringing the pure science part, the pure Western science part, to meet the pure Eastern sound part, and we're going to watch these two merge together. I'm going to lead you in call and response to this verse you see. Some of you already know, but I'll do a little part, and then you'll repeat a little part. Om, Om, Om. Vakratunda Mahakaya, Vakratunda Mahakaya, Surya Koti Samaprabha, Surya Koti Samaprabha, Nirvignam Kurume Deva, Nirvignam Kurume Deva, Shubha Karyeshu Sarvada, Shubha Karyeshu Sarvada, Shubha Karyeshu Sarvada, Shubha Karyeshu Sarvada. Om. 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 So Ken, Paras, and I started talking about including this event in this weekend a few years back, and every year it got a little bit closer. Every year it got a little bit closer until finally this past winter, it kind of all came together thanks to his great generosity and those who are going to be working with him today. I can only say that he's a brilliant scientist and a lovely Gurubai, yeah, we can say that. And so glad to have you here with your group and can't wait to get involved with it. Thank you.
Really a joy and a privilege to be here with you and with all my family here. Maybe we should make sure it's not too loud. And I'm going to, Seth? Sorry, I'm going to need to call up my presentation. How do I get out of this one? Not an auspicious start for a technology talk. There you go. We should not be taking that off the screen too quickly. You're absolutely right. Where is... And I have your talk, Nabin, and mine here. And Sarah, yours is on as well. So, play from start. Okay, I hope if there are any difficulty seeing any of the images, we can, if as needed, we could potentially turn the light down. But Seth was explaining that for people who are streaming in, the lights are kind of important. And I'm watching my little marks, Seth, so before, yes?
Who's controlling your slides? Do you need somebody?
Oh, I am.
Oh, you are? Should I? Do you want to tell me?
No, meditation, no. I wish one of these years, this thing. Too bad. So thanks. First of all, let me begin with a Jain, the holy mantra for the Jain, which is where my training was, to follow this beautiful mantra that Shanta gave us. Om Namo Arihantarnam, Om Namo Siddharnam, Om Namo Ayariyanam. Om Namo Uvajayanam. Namo Loe Savasahunam. Esho Panchana Mukaro. Sarvabhava Panasano. Mangalanam Che Savesim. Paramam Havai Mangalam. Om Shanti. So this is a really beautiful day for me because I've been coming to Ananda Ashram since 1974 when I was a teenager. That's me with the long hair. And this is my colleague Sambhav. Is Bharati here? No, she's not here. And Tara, you probably remember in the old days, my colleague, and we were students of a Jain guru in India and New York, Chitrabhanu. But we also came to love Dr. Mishra and this ashram and became part of this community over a long period. And then in later years, my wife Jayashri and I, who's standing in the back, this has become our family again and our home. So I have a long history with this ashram, and I've been for years sitting down here and talking brains and talking meditation, and I've done a few things during COVID where we did a Zoom meeting, but this is the first time that I'm here to talk a little bit about science and yoga and how they come together in my mind. And we have a lot to offer in this session with my colleagues, Nabin and Sarah. And we'll introduce each of us as we go through. But really the focus here today is on this question that I raised in Devan's extraordinary presentation this morning about how we understand the path of knowledge in the context of the search for enlightenment. How does science and yoga talk to one another? Bharati-ji, you're just in time. Bharati-ji, the old pictures, Sambhav and me. Can you see? We just started, don't worry. Oh my goodness, that's okay. Hello to those who are streaming in. We're not very formal people here, so you'll be fine. So what I'm going to do in my part to get us started, because as Shanta and I were thinking over time, the focus of this weekend really is on sound and Sanskrit, on meditation, and on language, and how we can integrate different approaches to understanding more deeply ourselves through the study of Sanskrit. Obviously, that's what we're here for. So in putting this presentation together, for my part, I'm going to first start by just a few remarks about how we might marry science and yogic perspectives, certainly how I have to, given the work that I do, which is in neuroscience or cognitive neuroscience, and where I think there is opportunity for cross-fertilization. But I'll make that brief. That in the past, that's been an entire talk, really, and we sort of alluded to it again this morning, where we were talking about what is vidya, what is avidya, what is right knowledge, what is the value in logic and epistemology in general. And I'll make a few remarks. Then I'm going to focus very briefly, thank God, I do this talk all the time in many venues, not on meditation, but on my work in neuroscience. I'm going to give you a very quick look at some of the brain imaging technologies, but I'm very fortunate to have my colleague at Yale, Nabin, who is not only helping to set up this actual data collection that we're going to do with this cool machine that NIH gave us, and demonstrate and try to get us all involved in thinking about how we might use it in a Sanskrit weekend. But he's also going to present, before we get started in that demo part, and maybe even an experiment we can design together. Nabin will go through some of the imaging technologies. I'll just do that briefly. Then I want to highlight areas where the neuroscience and yogic approaches have already been very effectively coming together, particularly the study of meditation or mindfulness, as they call it in the secular world. And there, my colleague Sarah Mulakutla, I always have this phonetic mixing up, Dr. Sarah Mulakutla, who is a neurologist and is now beginning a collaboration with Nabin and I at Yale, is doing amazing work on mindfulness and Parkinson's. So she'll talk a little bit about her work to give us a sense of how the science and medicine have come together. And then I get to really the focus of my presentation today, given the theme of the weekend, which is, what do we know about the brain doing language and music and cognition? And I'll mention things that are very relevant to what we're all doing, like what is it like for the brain to learn a second language? How many of you are native Sanskrit speakers? None. Not even Bharati. But we are all second language learners. And the work on the bilingual brain, which I've published some work in, is fascinating and really interesting when it comes from the point of view of how the brain strengthens itself, how it learns new connections. So we'll talk about things like that. Also, the focus here is on chanting as a tool to learn Sanskrit. And so I've prepared some presentation of some work on how the speech motor systems work, and we can actually see how the brain is doing this, and we'll kind of make the connection there. And then finally, as all of us know, when we study Sanskrit here, it's very useful to learn Devanagari. It's very useful to learn the written form. And so I'll be talking a little bit about how the invention of writing systems, only about 8,000 years ago, has a profound effect on how we talk and listen, how the spoken language brain. And this is an area that I do research in. I do work with children with profound language disorders and how to help them find their way forward. But it's also just a fascinating scientific puzzle. How does the brain, which has evolved to talk and listen, we don't need to go to school to learn to do that, how does it learn to read and write? In the context of this weekend, it turns out that getting the literate code, learning the written form, is very profoundly useful in learning a language. So we'll talk a little bit about some of that. And then finally, and I'm bummed that my friend Naren is giving a concert today, but he'll be here tomorrow and on Monday. I'll make a short presentation on music and the brain, and only just to make the connection between the language brain, which uses the same end organ as music, and how they overlap and how they diverge. And so as best I can, I'll try to share some of the science. At that point, I'll turn it over to Sarah, who's going to talk a little bit about meditation and Parkinson's and her own work, and how we're excited to be using some of these technologies together. And then Nabin will get us started by going through the imaging technologies, and particularly this one called FNIRS, what it is. It looks pretty unimpressive, but it's like really high tech. And so he'll go through that, and then we get to what we hope is the fun part, which is to, as a group, sit down and think about what kind of questions we might want to ask if we have a device like this. Like, especially in the context of this weekend, how does chanting affect language learning? How does the written and spoken form influence one another? How does, rote practice, how does learning grammar affect? So as we think through those things, and we do want to make that a group exercise, then we can actually put the caps on you, some of you. We won't have time for everybody, and start actually doing a mini experiment, the beginnings of an experiment that we could continue beyond today. So that was sort of the tease of making it fun, right? I basically will give you a lot of science, we'll give you some background. We're here in the context of an incredible weekend of learning about the Sanskrit language, and we can actually start to think about how we would use the device to to make progress in that area. So again, I want to be mindful of time. We have 3 presenters. We have a very long session, but we want to take a lot of that time playing with the cap and getting you to think about the kinds of questions you might want if you could peer into what used to be called in psychology the black box, the brain. In this case, it's a white box. But here's the big but. As in Devan's presentation this morning, as we exit our formal sort of giving you information part, I would love to go deep into discussions and debates and questions that'll help us to think about what kind of research would be meaningful as a group and in general. And we can really take a deep dive with questions as we did this morning. And we have plenty of time for that. Even as we're setting up the equipment and doing the demo, we can continue a discussion about neuroscience or science in general and yoga. So to begin, and I must tell you that my discussion of this is a very deep topic. I've spent my life trying to figure out how to live in yoga and in science. And I know many people here have similar experience. And it's a very deep topic. There are a lot of ways to approach it. But I just want to give you a sense of how these different approaches tend to be used, what questions are asked in cognitive neuroscience, which is my field, and what questions are asked in meditation and yoga centers like this, which is all our fields. Okay? So to begin, I would argue that our understanding of the human mind, of what it is to be a conscious, intelligent being, has benefited recently and non-recently by 2 very often unconnected frameworks. The first is the field that I work in, and Nabin as well, and Sarah is a neurologist as well, is been referred to as cognitive neuroscience, and that just means the study of how the brain does cognition. So we're marrying cognitive psychology and mathematical modeling with neuroscience. And the second is the ancient yogic traditions. I tried to immerse in several of them. I started out and spent a long time immersing in the Jain approach. But one of the things that we tend to ask in cognitive science that makes for a difference, it's not a difference in some fundamental way, it's just where the focus tends to be. So the focus in cognitive neuroscience tends to be on how gene, brain, cognitive, and environmental factors produce who we are as thinking, perceiving, remembering, and attending beings. And the focus in yogic traditions, as we all know, is not just on how we think, remember, and meditate and quiet our minds, but how well could we improve the way we interact? How can we gain insight into how to better interact with the world? So in many ways, and perhaps, improving perception, attention, and cognition. So this is not a fundamental difference. You can do both in either. What it is a tendency of focus. In science, the focus tends to be on questions like this. How does the brain give rise to thought? How does it break down in disease state? And how do we fix it? And a lot of my NIH research and work Sarah does and Nabin involves using this approach to better understand how atypical brain development happens and how we can, by understanding the biology as well as the cognition, how we can potentially improve outcomes. In my case, in a pediatric population, children. In yoga, of course, we ask a different question very often, which is how well could it work, as I said before, if we knew how to better harness its immense capabilities. And of course, as I've alluded to at the beginning, science and meditation have found a very happy marriage in recent years. A couple of other things, just as background. In terms of science and yogic search, the search for what is real, the core attitude in the search for what's real, whether you're doing it with these devices or with your eyes closed and your mind turned inward, is to understand and to take joy in understanding. We tend to use a word a lot, and of course it's a word used in all schools, but it's a big word for Jains, pramana, which means valid knowledge or accurate understanding, both of the physical world, which includes the brain, and also of knowledge and knowing and logic and consciousness. So there is one difference in if you live a life, as many of us do, where we work in science, but we want to also go into whatever you want to call it, enlightenment somehow. That's what we're drawn to. Because in science, we have a method, and it's a powerful method. It's a very useful method, as you know, that allows us to observe, to generate hypotheses, to test them, to refute them, etc. Which means that any question that is in the purview of science must be able to be turned into numbers somehow. They must be measurable. So questions like, what is transcendent experience? What is non-dual awareness outside of its sort of neural correlates, of which there's some work? That question of that deep inward turn that we all are doing here is difficult to put numbers to, frankly. It's difficult to measure. So much of yoga and meditation and yogic philosophy, Samkhya, Jain, Buddhist, Vedanta, all of these traditions have much that is measurable. That's why people are doing brain imaging of meditation and such. But there's questions that we ask in the privacy of our meditation that are, what happens when we shut it all down? What is valid knowledge without concept, without form, without words, without language? And so, in many ways, these are not, in any sense, conflicting. They often become conflicted in like misunderstandings. Oh, I'm a scientist, I'm not after that yoga stuff. Or I'm a yogi, I don't need science because it's all Maya. And if it's all Maya, who wants to measure it? That's why I was asking you, Devan, about avidya. And that's just not right. That's ridiculous. If we are truth seekers, we want to do everything well, whether it's measuring brain activity or cell division or sociology, as well as what it means to be in a place that cannot be put into word, that is ineffable in some sense. So in all of the yoga traditions, there is a history and an emphasis on the path of jnana, okay? As one of the ways in the school, certainly in the yogic school, in the Vedanta school, it's one of the core paths. But you see that thread in all of the traditions, especially, Eva, you'll remember this, the Jains are like jnana on crack. We Jains are crazy for jnana. Are you Jain by any chance?
He's a native Jain.
Oh, Jai Janendra. What is jnana? Well, there's a question for a lifetime. But of course, it is, in some sense, seeing and understanding what is real. So understanding how physical systems, such as brains, work can be either pramana or apramana. It can be valid knowledge or understanding the world that our senses provide and our inferences unfold can be pramana or apramana. And our goal is for pramana, for a valid knowledge. And in the same way, when we go to that thing that can't be put into words or measured, we still have the same goal, which is to understand, to get valid knowledge. But when it comes to much of jnana yoga, much of epistemology in these ancient approaches, from theories of how we know and logic, and again, Devan beautifully alluded to some of those epistemological truths. By the way, I found it just beautifully fascinating how you brought out the point that ethics could only diverge from other areas of philosophy in the West and not in the East. It's an I'd never thought about that, but clearly in the Eastern traditions, in some sense, it's more integral, it's more hidden or more obvious. I don't know, but it was an interesting point. Anyway, back to this. So the scientific method is a powerful tool. And again, in each of these approaches, whether it's Ashtanga Yoga, whether it's the Buddhist Eightfold Noble Path, which I've been much thinking about in the last few years since meeting a teacher in Taiwan, or the core Jain teachings of Ahimsa, nonviolence, Anekantavad, which is actually a kind of intellectual humility, an idea that valid knowledge can only occur in parts, and nobody through the mind sees all the parts, so we have a kind of relativity. The Jains also have a notion, for those of you interested in epistemology, of what's called Nishchaya and Vyavahara, Nishchaya being a kind of a kaivalyam, a kind of a deep knowledge, seeing all angles, but all perspectives, philosophy, science, art, poetry, sees reality from a different angle, and none see all, as long as there's a conceptual frame. And then, of course, the Jains love to suffer wonderfully, fast a lot, and not eat or talk. And so there's this aparigraha and svadhyaya in all the ancient traditions, Vedanta, Buddhism. Svadhyaya sits at the center. They call it different things, but it's essentially, who am I? Self-inquiry. I just want to take 1 second on this slide. And again, as a background for, because this is the one that I grew up in. So in the Jain epistemology, very similar and having some interesting differences with Samkhya and more differences with Vedanta, but similarities. The Jains would talk about jnana or valid knowledge as having 5 stages. Now, I'm not going to go off on a Jain lecture, but I want to share something. The first kind of knowledge, they use the term paroksha for what they call mediated or indirect, and in this case, it's mediated by the senses. And then they also believe in a kind of knowing that is not mediated through the senses, but in a sense is insight or non-conceptual, and they call that pratyaksha. So it's a different use of those terms that you might see in Samkhya. But the key point is that the Jains and many other schools think that if you're going to live in a body, in a world, in a senses, and you're going to want to understand who you are, you want to understand the world as it is, right? There is a sense of realism that, yes, everything might be not fully understood, but it's not purely Maya. There is existence. And so there is a value to getting accurate or pramana for the senses, mati, for inferences and verbal extensions, conceptual extensions, shruta. And then in each of those areas, the Jains, in sort of the proto-science of the Jains, really went crazy on everything from biology to epistemology to logic to mathematics. And the idea is that this is not the deepest knowledge. This is not that transcendent knowledge. But if you're going to do it right. And then you consider the other kinds of knowledge which are entirely outside of the purview of science because they're not measurable. Avdi, Manaparyaya, and Kevala. And Kevalya in Jainism is very similar to its use. Okay, so science and yoga. Similar attitude, which is to love truth above all else, I suppose. Different measures, because science requires something that is measurable, or else science is not antagonistic to it, it's just simply not part of it. And yoga, which has much of science, but goes somewhere else. So this is a time where we can actually bring these technologies together. We can now observe and measure the living, dynamic brain while people are doing things like reading, writing, thinking, remembering, or meditating. And cognitive neuroscience and its methods, so here's where I get a break for once, Nabin, because he's going to cover this as he introduces you to the technology. But neuroimaging is an umbrella term that refers to the many ways we look at the brain's structure, its gray and white matter tracks, you'll see. Its chemistry. In my lab, we do something called spectroscopy, magnetic resonance spectroscopy. We measure the neurochemistry of the child's brain and as they grow and as they undergo different kinds of treatment, learning. And then functional imaging. And Seth, could we kill the lights just for this, my friend, please? This is why I came to this. You're going to love this. Okay. This is from Adam Ghazali's lab at UCSF. He's a very bright guy. He does amazing work. This is, oh. You're completely off camera. Yeah, I know. That's okay. I want to watch it. And the people, unfortunately, Seth was saying the people who are zooming in can't quite see this. This is your brain. It's called, just watch it. This is what it's like to be living and thinking right now at this moment. And what they've done is they've created something called a glass brain fly-through. That's real data. That's brain activity. And these little squiggly lines through there, that's the white matter tracks. And then this is a computer reconstruction so you can see inside. And so if I'm sitting here liking the lunch or doing the Jain mantra, all of these things are firing. And what I want you to appreciate, now he's sort of going into the inner parts and all the white matter tracks. So this is your brain on whatever, cognition.
That's electricity, right? That's what
Yeah, those are, yeah, of course.
electrical signals that between fibers that connect different areas of the brain.
Exactly. And our neurologists can, more quickly than I can, identify which parts are which. So why am I showing you that? Well, I think it's a miracle, okay? I'm sitting in this 86 billion neurons, give or take, in this little bit of flesh. And I like that umbrella, but I don't like that car. And I want to go to school, but I also want to go to the beach. And everything else, and I want to understand what's real. And all of that is taking place in this complex, you ready? Nonlinear, self-organizing, dynamic system. So when we model these things, mathematical models, we're looking at, and it's all taking place in real time. That's what your brain looks like right now, or when you're meditating. How do you think it might differ when you meditate? Maybe, well, not quite. Otherwise, you'd be like dead. But you're right, of course. It will change in some important ways. Okay, so just one brain imaging demo for you guys, because we very often use something called functional MRI, and the device that we're using today is kind of a portable, something we can take into schools and clinics and ashrams, and it gives us similar data. But what fMRI tells you, and again, Nabin will cover this, areas of the brain that are active when you're doing something, like think of a pink chicken, you think of a pink chicken, and some brain areas light up. The pink chicken area, no, there is none. All of that involves neurons firing and populations of neurons exciting and inhibiting one another. And then there's a kind of a hemodynamic, a blood flow shift, and we can measure it. So look at this prototype experiment, because you're going to design an experiment today as a group. So here's the easiest experiment on the planet. You ready? Condition A, open your eyes. Condition B, close your eyes. Condition A, open your eyes. Condition B, close your eyes. Now, what this does is, with fMRI, we will identify those populations of neurons in the brain that are increasing their signal when your eyes are open and decreasing it when you're closed. And you know where they are? If any of you, where does vision go? What part of the brain? You know this. And that's the occipital lobe. in the back of the head. Okay? So that's what the data looks like. And again, Nabin will show you the various approaches that we take. Another muy importante thing for this. When we look at that brain that you saw, the fly-through glass brain, what you're seeing is that it's not any one part that makes us who we are as thinkers and understanders. It's the way in which they're talking to one another. In the technical world, we call that functional connectivity. It just means the degree to which different parts of the brain are operating as a circuit, are operating together. And it turns out that when you study meditation, and Sarah will address this a little bit, which, by the way, has turned into a cottage industry in science. And in the last 10 years, the number of scientific publications has exploded because people in the West began to understand that we have a very anxious world we live in, and we really need to do something about it. And so, what is the research? There's a good friend of mine named Richard Davidson who does extraordinary work out at University of Wisconsin, has written eloquently as well as published hundreds of papers on meditation and the mind using these tools that we're bringing to show you today. A lot of the basic science of meditation, like you're kind of a happy young brain and you're not struggling with anything, and we're going to understand what happens when you meditate. A lot of that work has been focused on what is called neuroplasticity in the popular media, okay? Which means in different ages and in different ways, how much can the brain rewire itself, okay? So the basic science of studying meditation, which has been very fruitful, I think, and continues to get fruitful, is to understand brain plasticity. For example, old people like me learning to meditate, their demonstrable benefits seem to be emerging. And of course, Sarah will talk specifically about a neurodegenerative population where meditation is helpful. So the basic science, though, is to understand the brain. And in yoga, it's to get samadhi. But they ain't enemies. They can be allies, I think. In this biomedical world, though, in the clinical world, where I do my research and where Sarah does her clinical practice, we're often asking the question, can we improve something by these approaches? And there's really been a big focus on meditation. In the secular world, what Richie Davidson and John Kabat-Zinn and others had to do is, in order to have the medical world not see this as some, oh my God, it's another Eastern thing, is this like the TM guy kind of thing, they had to kind of divorce it from its deeper yogic context. It's more secular, so they call it mindfulness. But of course it grew up where? It grew up in our traditions of deep meditation. And then it had to undergo its test by fire. Is it useful? Does it have an impact in medically relevant conditions? Most of the research has tended to focus on things that they call, the secular words for this are focal meditation, which means like watching your breath or a mantra. And then there's open meditation, which is witnessing and things like that, vipassana. But there's been a ton of science on this. And this talk is not about that in great depth, but I want to introduce it because it's part of what we're here this weekend to do. We are using Sanskrit to improve our meditation, to deepen our meditation. So I don't want to leave it out. And again, we want to talk a little bit about it. So the evidence is pretty good in the last 10 years for a lot of plasticity and benefits, especially on mood, anxiety, depression, pain management, and attention, which are like all pretty important things. This is a beautiful study that Davidson's group did years ago where they actually had people in a 3-month vipassana kind of training, and then they were looking at the brain's ability to select and focus and using brain imaging and cognitive tests. But here's what they found. that the ability of the brain to stay focused on target, unsurprisingly to those who practice meditation perhaps, was very much enhanced in measurable ways with the brain. And where we see changes in the brain's function, we also see changes in the gray and white matter volume. We're not going to get into that in any great detail. And as I mentioned before, what really is interesting in mindfulness research is that we're now seeing that when the mindfulness is effective, when meditation is effective, especially in anxiety reduction, which has known physiological pathways, when it has a positive impact, it is through changing which parts of the brain are hanging out together, kind of. So it's very much a systems level work. So for those of you interested in this, this is just an introduction, but we can go much deeper. And here's the, along with what Sarah's going to mention, there's just really a growing evidence on effects on mood and on anxiety. I did a talk here, I think, a year ago or so on anxiety in the brain and its basis, the HPA axis and all the rest of it, and how meditation research has been productive. So, to get to the last piece, I started by saying how science and yoga go together, with some slides, and way not enough information. I hope over the course of these hours we can come back to that question. Where do science and yoga come together? Where don't they come together? Where are there opportunities that we're missing? But I wanted to give you that overview. Then I wanted to talk a little bit about meditation, and I'd like Sarah to kind of talk about her work with Parks patients. And then we're now going to get to the sort of the rest of my presentation, and hopefully the kind of experiment that we would design, which is, what do we know about language, music, and the brain? I was so regretted I gave you that title. Because it's a big topic. So first of all, language. What's special about it? Well, for one thing, and I would argue this quite strongly, Seth, you might have read on this as well, but I don't believe that any other species has proper language with syntax and grammar. This was much debated and much researched by friends of mine from Columbia and other universities over the last 30 years. But there is a sense that language is not communication. All animals communicate, and some of them do it in a very sophisticated way. But language proper with all its rules, language, as Bharati will tell you, and phonetics and grammar are almost like genetics. You have a number of primitives, and then you have an endless number of permutations. It's rule-based. It's built into the wiring of the brain. We have it from ancient evolution, and it's special. And we do not see, to my estimation, as somebody in this field, anything convincing to say that it is not uniquely human, even though animals communicate wonderfully well. But that's something we could take up if you're interested. And language has been around for a long time. So that is a larynx, and that's not a man, and that's a man. And this is what? What is that? Yeah, go ahead, please.
I don't want to completely open up the can of worms about language and
Sure,
animals
no.
and stuff, but I just have a question. You're so definite about that. And for example, birds communicate, vocally,
Yeah.
and they make sounds that human beings can't make, and they're
Indeed.
very specific. And if they don't learn it from other birds, they won't communicate correctly, and they won't be able to get a mate.
Exactly.
But why do you not consider that a language?
Well, so first of all, this is always going to be an open scientific question. And science doesn't work in absolutes. It works on probabilities and research and data. And I would say that the people that I think have approached it most deeply, this is not my area of research, even though I map the brain. especially for language. I feel that the evidence at this point is consistent with the claim that some of the what are called the mathematics, the computation of language has certain elements that are not present, that are necessary. For example, sign language. It was much debated. I do work, and as does Nabin, on deaf cochlear implant recipients and signers and their brains. We can talk about that later. But we have evidence that sign is, in fact, a proper language. So what the birdies are doing is very much like language. And let's come back to it. Let me just say one thing. There are no authorities on this, and certainly I'm not. But my read of having spent a long time in this field is that there's something just a little bit like it's not just like the brain keeps getting more complicated and it just keeps getting more and more complex language. There's a kind of a jump, there's a step that we think requires certain things in brain development, which I do have a couple of slides. But let's come back to it. It's a good question. Well, go ahead.
Hi. Is there any evidence on how the beauty or the sweetness of a language is perceived across cultures? Because I understand that the last best language or the sweetest language chosen was Bengali, but I'm Indian. So for me, I don't know how they could consider Bengali over Urdu. So I don't know if
Jayshree and I love ghazals. We love to hear the Urdu ghazals.
Is there
It's a beautiful
standard
language. That's a great question. Let me just say this. Language has many functions. One, and most important, is communication. In fact, one of the things we do now with brain imaging, in case I forget, is we put caps on me and caps on you, and as you and I talk to one another, our brains become correlated. They become entrained to one another. So, of course, the first function of language is communicative. The second function, and some debate, maybe even a more evolutionary earlier one, is that it allows you to represent the world in symbols. It creates a kind of conceptual knowledge. All of that is part of what language is, but language also conveys emotion, and it conveys warmth and distance and love and hate, and sweetness and non-sweetness across languages. And the brain pathways, we can map them, you'll see them, but the question of what constitutes the sweetest language or something along those lines is very subjective. I'm not enough of a linguist to be able to say, so maybe Bharati, for example, as a proper, oh no, she won't let me say this, but she knows everything, about what languages are most beautiful to listen to. I'm not leaving you out, okay? Anyway, we'll come back to you. Okay, so let me finish this off, okay? So language began in the species, and whether it's a non-monotonic jump or it's a linear relation, it goes back around 30,000 years. And what that means is, and for those of us who study the brain, we've created a whole lot of biological specialization for talking and listening. That's why babies, well, you'll see in a minute. Written language is a relatively recent invention. The taking of natural language and representing it in a written form. Anybody know what that is? Somebody, of course. Rosetta. And this is the larynx. One of the key things in the evolution of human language, which many theorists have argued started with hand gestures, like sign, that are shared with other species, and then with the dropping of the larynx in human evolution, which is why I have this picture. Sorry, I'm in Nerdland. I promise I'll come out fast. Is where the complex articulation that Bharati teaches us. Now I'm not allowed to say your name. Bharati teaches us the phonetics, ba, da, ga, stop, consonant, velum, all of that depended on the evolution or the dropping of the vocal tract. And in many ways, this is it's ancient, but it's not so ancient. But writing is like a pipsqueaky kid. It's only been around for 7,000 years. Okay, so some cute slides. I hope you like them. I stole them from my Taiwanese colleagues. You have, the evolution of the species and the development of the brain and its folds and its complexity. And I know that this comes up a lot in our Sanskrit class and in this discussion. Where does Sanskrit fit in the world languages? And how do we even think about where languages come from? Now, I don't dare, I heard you talking about it, Devon, I don't dare get into what's the oldest language. I would defer to you, my professorial friend. It is, of course, a fascinating field, the evolution and migration of languages. And as Devon can tell you, it's an area where now it's brought many new tools. These are some of the categories. There's the Indic languages, the Eurasian, the Pacific, the Dravidian, et cetera, et cetera. The world languages, Sanskrit sits as one of them, but as we know here, it's something very special for us. But how do we actually understand, Bharati and I also talk about this a lot when we're hanging out, like, what's early, where does Sanskrit come from relative to the Persian languages, et cetera. There is a whole field of evolutionary linguistics that I wanted to show you a slide, in case you're interested, which is combining genetics, actual genetics, so where your genes come from, and then combining it with linguistic analysis to try to trace in a more precise way how migration of peoples and the genes that they carry with them are related to the evolution of languages. So if you're, again, because it's about language and it's about language writ large, I thought you might enjoy to, kind of see that there are people who spend a lot of time thinking about where it comes from in the species and also where it comes from in our history. But I got to tell you one thing. Because language is so old and it's been around so long, we have a lot of brain specialization for it. So when a baby comes into the world, to put it in a silly way, you don't have to teach them that that's ba, da, and ga. They just need to be spoken to. But it turns out that babies, as in Pat Kuhl's work at University of Washington, are showing evidence of being tremendous little linguists as they pop into the world. So what happens is, if I play to a baby, newborn, any sound contrast, like ra-la, or the Hindi dentiflex, da-ta, or anything else, and the baby hasn't spent a lot of time in one language, no language, their brain is capable of hearing all of that. And it's only after they spend 6 months to a year hanging out in English or Japanese or Chinese or Hindi that they begin to lose sensitivity to non-native contrasts. So the brain starts out with this massive pool of ability to make discriminations, and then it sort of prunes away in order to use the ones. That's why if you know that in Japanese, it's very hard to hear the difference between ra and la, okay, and the Japanese speakers often. It's very hard to teach that, so people have done, my silly world, like 50 hours of brain imaging and teaching to see if adults can hear that. It's very hard. It's hard for me to hear, oh no, Jayshree yells at me all the time, oh no, da, ta, ta, because it isn't in my early experience. But anyway, the babies will hear, the Japanese baby who hasn't heard a lot of Japanese yet, will easily perceive those distinctions. But then after they spend 6 months to a year listening to Japanese, those things begin to go away. So why am I showing you that? Just to give you a sense that even the infant comes into the world with extraordinary capacity to learn. Now, the language brain involves, what part of the brain does language, what hemisphere? The left, right? So that's like pop psychology in a sense. It's true and it's not true. There is a whole lot more biologic machinery, as you'll see in a second, that goes into the left hemisphere, but it's also present. Language has presence in both hemispheres. But the left is special. in a lot of ways. And there are a number of important regions. I'm not going to go into these in detail, but we have areas that are critical for producing language in the inferior frontal, the premotor areas. There's no quiz on this tomorrow on the neuroscience. And then there are areas in the temporal and parietal cortex that are very important for perceiving or understanding language. So receptive and expressive language systems. Now, this is just to give you a gestalt. This is a very, very careful analysis by Kathy Price at the Wellcome Center. And again, we seem to be covering it with the light, but there's nothing we can do. You can see that, if you can see this at all, there are a lot of areas that are dedicated to auditory language, to sentence processing, to connecting print and speech, to producing language. And we know a fair amount about how these are laid out and how these are localized in your L1, your first language, when you master it. And of course, we know from brain injury that if you damage any one part, you're likely to lose very specific aspects of language. Now, I hope you can see this, but I don't have a video, so this is meant to show you what happens. Remember how I showed you the brain spinning around and all the activity? So if a word comes to your ear, like cat, what's happening in the first 55 milliseconds? Now, sorry guys, 1,000 milliseconds is 1 second. So 55 milliseconds is like a blink of an eye. So what happens is your brain begins to light up in the auditory parts, because that's where the sound goes. And then a few hundred milliseconds later, which is not a lot of time, you start to see activity in Wernicke's and Broca's and other extended areas. And then it continues until you suddenly get cat in your brain. So this is kind of the real-time unmasking of language. And I want to show you, if we do, like, for example, just ask me some question, like, where do I come from?
Where do you come from?
Elmont. So what happened when I heard his questions and then I wanted to, this goes to chanting. This is what underlies chanting, if you will. So when I'm trying to think, where did I grow up? I can't remember because I'm getting old. There's a conceptual process that involves a lot of middle to inferior temporal regions. Then I start to think about how to say Elmont. And we start to see an increase in activity in the Wernicke's area, in these perisylvian regions. Then, why is that not doing? Then we're trying to think about how to pronounce it, or maybe to chant, or to start to sort of recite something. So we have activity that shifts to the parts of the brain that control the vocal tract. And then we sort of have to plan exactly how to Om Namah Shivaya, Om Namah Shivaya, Om Namah Shivaya, Om Namah Shivaya. And finally, if I say something like, I pent to the wool, but I meant to say, I went to the pool. There has to be something in the way that the language system works in real time where it detects errors so that we can adjust. So if I'm not chanting too well, I'm making mistakes, David's going to get mad, then there has to be a kind of a feedback loop. And that feedback loop is here. So when we talk about what it means to chant, what it means to produce language, there are a fair number of important areas. Maybe we could study those areas. Finally, a few other things briefly. I know I'm gone over a bit. We do have a long session, but still, I want to turn it over to my colleagues. I just want to make a few final clarifying points. One of the questions that often comes up in studying Sanskrit is how important is it to learn to write and to read? And this is an area that I spend a lot of my professional work, not in Sanskrit, but in children. How does learning to read change the brain? So if areas of the brain that are involved in expressive and receptive spoken language. We just showed them, right? All these areas. Those are your sort of general language machinery. And in order to learn to read, we need to suddenly recognize that the word cat, of which I know how it sounds and I know what it means, right? That somehow it can be represented in alphabetic languages by the letters, or in Hindi by aksharas, or in Mandarin Chinese by phonetic and semantic radicals. And so I need to build that into my brain. And it turns out that building that into your brain, as my work and also Stan DeHaan's work shows, when the brain becomes literate, when it learns the literate form of the language, that actually feeds, it not only depends on whether the oral language, the speech is okay, but then the speech actually gets benefit. So strengthening the written code actually strengthens the oral code, which is another reason you would think in learning a second language, really immersing in its literate form, its written form, is important. And this is stuff that we've worked on for some years, that the development of reading not only depends on speech, but it changes speech. And if you're learning a second language, it does so as well. Now, this is just a few more slides. One of the questions we might ask in this weekend is Sanskrit different than other languages in terms of which parts of the brain are involved? Since parts of the brain kind of matter. I hope I've been sharing that with you. Or is it just the way those parts are working rather than where they are? So we don't have any data on Sanskrit, but this is a study we published some few years ago where we looked at how the written and the spoken language builds in the left hemisphere in Spanish, English, Hebrew, and Chinese. And the take-home from this study, which was really very striking, was that at the level of the brain, the way these dual systems built was not in any way different from one language to the other. So the machinery of the language system is the same, but what you do with it, of course, is going to change. Finally, learning Sanskrit is becoming a bilingual, and there's a lot of work on bilingual brain. And I'm just going to not do it much justice, but very quickly mention that when you have a bilingual experience, when you're learning a second language, there's growing research, and that seems to be reliable so far, that the second language can have a benefit on cognitive aging. Okay, in other words, it's sort of strengthening. There were for many years an idea that bilinguals have better executive function and sequencing skills. Unfortunately, that doesn't seem to be holding up. But there is evidence that you're strengthening the brain in ways that are prophylactic with regard to aging and dementia. And in the same way, becoming a bilingual is actually, not surprisingly, strengthening the brain's structure and its functional connections. And just to show you that the Devanagari script is not different, this is a paper that I did with colleagues at the National Brain Research Center in India, in Delhi, where we were looking at bilinguals and biliterates, people who could read and write, speak Hindi and English. And what we found is, depending on what age you learn the second language, you end up using slightly different connections, but you end up in the same place. So, and what was beautiful about this is that when you become really good at integrating these languages, you're strengthening the oral part. You're strengthening your spoken language part. No, these were young adults who were either learned to read both languages at the age of 6 or learned to read them 5 years apart, and then we scanned their brains as young adults. And they were all good Hindi and English speakers and readers, but what we found is that, I can go into that. Let me just finish up. Sanskrit immersion, I found one paper, Shanta, on Sanskrit in the brain, and it wasn't really Sanskrit. But it was a recent publication in a fairly good journal by a group in India who were looking at Vedic priests who spend their entire lives immersing in Sanskrit and memorizing it. What do you think that's going to do to the brain? it does. In a sense, the brain imaging is not surprising here. It shows strengthening of a lot of these connections. But it is at least the closest thing I could find in the science on Sanskrit. Now we get to the last thing, and this is where I need that. And I'm guess it's only 2 minutes. I can't do music justice. You know who can? Music and science, Naren. So when he comes back tomorrow, we're going to bug him. But I'm going to show you a couple of things about music and the brain in the context of how we're chanting, and then I'll finish up. I'm done. Okay, are we hooked in? So this is a colleague of mine who's at University of Connecticut, Ed Large, and he studies the neuroscience of how people become, how they learn music and how they respond to music. And there's a big question. Do music and language talk to one another in important ways? I'll end with that. But music itself is fascinating. What does it give us? It gives us everything, including profound emotional experiences and memory. This is your brain on Chopin. Now, what you're seeing is as you reach different parts of the emotion, you're beginning to see the activation of emotional responses. I just find that cute. This was a combination of, it's mostly EEG for this one, but then he mapped it into the MR space. Okay, so the last two things, music. What do we know about music? Well, like language, it has a complex organization, and many parts of it overlap with language. It has very strong connections to the limbic system, the emotional system. It is very good for evoking memories, as you know, and also for emotions. But interestingly, when you look at music and speech, what you can see at a very fine-grained look at the brain is that while they activate the same broad networks, they actually separate from one another in important ways. And so they're working in concert, but they're learning how to separate from one another. And the last slide is just, again, a slide that I got from the large group. There's really good work out of his lab and many others on music and cognitive aging and dementia. This is a work on Alzheimer's. Engages patients, evokes memories, decreases anxiety, stimulates brain regions, rhythms. So, to end, and I'm sorry for going a bit long, immersion in Sanskrit. Well, learning to read and speak Sanskrit, like other second languages, is going to confer benefits to brain health. It must, and it will, like other languages. So there, I don't see a difference, just at the level of, well, the brain is going to, or how we'd learn it, like using or chanting is a very good means. Using writing and reading and connecting them is a very good means. But ultimately, like other L2s, it's just beneficial. And the integration of speech and print is very important for strengthening in the brain the expressive and receptive areas. And the memorization of sacred texts will surely make you a stronger memorizer, and your brain will get fatter in important areas, which is great. But that's not different than learning Spanish or Hindi or Finnish or any other language. And I think in this meeting today, and as we go into the mapping and designing a study, we have to ask ourselves this. There is some, and Dave alluded to it this morning, there's something special about Sanskrit learning that is clearly more than these neurological markers. Something that confers a spiritual benefit that is not easy to quantify, and brings us back to where I started, which is that the science will tell us a lot. I know that I can help people by learning Sanskrit, and I can improve their memories and things like that. But also, as we all know, by learning these texts, by learning to meditate, we do something that cannot be put into terms, cannot be put into numbers. And Sanskrit is special, and I wouldn't want neuroscience to trivialize it. It will use similar pathways. It's possible there's some unique areas. I doubt it. Possible. But it is something so much more than science can ever hope to. It is the vehicle for transcendence, as Dr. Mishra said. Sanskrit, meditation, and transcendence, and I'm not separating Sanskrit learning from meditation because at this ashram we do them together. And as we know, like Krishnamurti wrote, the highest form of intelligence is when there is no thinking and no evaluation. Through the narrow lens of conceptual knowledge and measurable knowledge, we can't appreciate the vastness. And to end with Dr. Mishra, you can't understand anything without going beyond the body and the mind. When you go beyond your body and thinking mind, then you will understand what's going on in your conscious, subconscious, and superconscious mind, because you are their witness. The witness is always beyond time and space, while the doer is always within time and space. So again, we have a very fruitful opportunity, and I believe for the ashram, to use science in ways that can help people and can inform our understanding of what we do, and maybe even improve how we teach. What's the best way to get this into your brain, to make it stick and hang there? But ultimately, the science is a vehicle to get us to a platform, and at some point we have to jump off into something that is clearly beyond science. Thank you for your attention. Okay, so now what we're going to do is I'm going to introduce the next part of the presentation, which is just an overview of Sarah's work with Parkinson's and meditation, again on this theme. Then Nabin will come up and he's going to show you a little bit about the technology, and then Nabin and I are going to be here setting up the equipment, asking for volunteers, especially people with short hair. I don't know, Nabin. Doesn't matter. And what I want to do when we get to that point, if you're with me, for those of you who care about this at all, is I want to talk a little bit about what kind of experiment we would design together based on your questions. Where might this technique? So let's switch to Sarah, and then we'll switch to Nabin, and we'll take a break, and then we'll start the brain imaging part.
Anybody needs to stand up and stretch, feel free, and you may be standing during my talk. This is a long presentation, so it's all good. Do you want to check my mic? Why don't you switch me to check my mic, and I'll put my presentation up in the meantime. Okay. Is my mic on? Yeah. Okay. Maybe.
Let me just say while she's setting up. So Sarah did her medical studies at the University of Stony Brook University, and she did her at Yale, where we are. And she is doing extraordinary work with patient populations and mindfulness, and beginning a collaboration for using brain imaging with us. We're really excited to have you, Sarah.
Thank you. Well, is this going to show up on the screen?
Oh.
I don't need the volume, but is this only set up for PowerPoint? Or, let's see.
It shouldn't be.
Is it? It was showing. Oh, maybe it's it's off the screen. That's really interesting. Okay. That's it's the screen extension. That's interesting. Okay, we can do this. Let me see. I should be able to make this really big. Okay, I'm doing PDF. Okay, we're gonna scroll. This is kind of interesting.
And her mic is going. Okay.
Hold on, I need to find this. This is actually a little tricky with the. Oh, there it is. Okay, I just want to be able to scroll. Okay, yeah, this is good. I think this is good. Okay. I might ask you when I'm ready. Oop, this is not a good. I don't want that square there. Hold on a second. Where is that cursor? There you go. And this one. All right, that light. Now let me make it. I think that's the biggest it's going to be. Okay, that sounds good. Okay. Oh, thank you. Let's see, this is light. Okay, I see the light is on. This is good. Yeah. Yeah. Or do we move the, yeah. Alrighty. Can we move that projector just to avoid the, I think so too. How about, wait, can I try this? I'll put this there. What if we go like this, like that? Let's see, like that. Yeah, projector angle. So can you, okay, that's fine. I want to put, can I borrow your book to put underneath it? Would you be okay with that? I'm gonna, because it needs to be up a little bit. Yeah, maybe. I have to ask Ann. Oh, and I touched something. Oh, what did I touch? That's what you don't want to do. Okay, well, it's a finicky connection. Let's do that.
I lift it and you put it under?
Yeah, you lift it and we put it under, and let's go like that, yeah. Okay, I think that's okay, because I'll get the brain imaging. That's the show, okay. Okay. Nice. That looks good. Oh, wait. That was what, a cloud? I think. Oh, wow. What did you say? A little bit? You don't need that. Yeah. I think I think this is okay. They covered someone got on the roof. Someone went on the roof. Yeah. I think so. Should we remove the chair? You think remove the chairs now? Okay. The slide? Yeah. Okay. All right, good. Okay. All right. I wish we had done that for Ken's presentation. Yeah. Yeah. Yes. Okay, sounds good. Okay, don't go in front of the blue. So here. All right. We got all this coaching. Okay, let's begin.
Sarah, I got to meet Maya. It's Archie.
Yes.
She's beautiful. Oh, she even spelled her name for me.
Yeah, yeah. Oh, I know. I heard you were here. I heard you both gave a fantastic concert on Thursday night.
Thank you. It's so good to see you.
Oh, it's
I
okay.
want to talk with you.
Okay. Okay.
Because there's a link with
Oh, good. Wonderful. Yeah, for sure. Yeah. 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 That's correct. Okay. Yeah. Oh, John did? That's good. Are you blocking from people behind you? I think it's okay. Don't move. Yeah. We're live. Okay, so we go ahead and get started. I think we can go ahead and begin. I am deeply grateful to be here today, not only to Ken for including me today. Oop, there goes the cerebellum. That's the one thing about this brain model that I have. All right, let's put that away. Not only for including me, but for our very inspiring conversations that we've had since we met earlier this year. Or early last year, I don't remember when it is, but also for Guruji, for Ananda Ashram,
for this deep-rooted commitment to yoga and science, which has shaped my own career. I grew up what I thought was a scientist when I discovered yoga, and it completely changed my perception of the world. I'm going to be brief about this, but I think it's important because it shapes a little bit of what we're talking about today. When I discovered yoga, and I was about 21, just after college, it completely changed my perception of the world. And after that, it was a little bit of an identity shift that I went through at a young age. I was in medical school and struggling with still this identity, this shift, as Ken mentioned, this divide a little bit between science and yoga that was so meaningful for me that I discovered Ananda Ashram. In medical school, I was in Long Island at that time, so I was searching for an ashram, and I came up here. And very quickly after I came up here, some of you know the story, but I was invited to start giving some lectures on meditation and the brain. This was 2010 at the time. To give a little bit of context to what Ken has shared with us. The MRI images that we are going to be looking at, the technology first developed really in early 2000, functional connectivity of the brain. And that was when the science of meditation could really start to be elaborated. So it really is a very young and nascent science. It was 2010 that I was in my final year of medical school. I came up here. I came with a stack of books in my car on all the books that were sharing about it. And I had a conversation with somebody and said, this is fascinating. People want to know about it. Let's have a lecture about it. Came back, you're on the schedule for tomorrow. So we had this informal discussion where I brought up whatever I knew. That transformed into Yoga Neuroscience series that actually my husband Hari and I conducted for about a year or so. We just went wild having these conversations. Can't believe I never met Ken during all this time, as of 2011. But that also inspired me to carry it through my residency training, the fact that there was some substance there. So I was presenting posters on yoga breathing techniques for residents, and believe it or not, my professional neurology society was really interested in it. They invited me to start teaching meditation to neurologists. I mean, who would have thought? Somebody I was so scared about, this new perspective that turned out to be my invitation to what is now my career. So what I'm going to talk about today, very briefly, has been the foundation of what I call a neuroanatomical approach to meditation. And then I will show my more recent work with Parkinson's, and I can talk a little bit about dementia and what we know, and I'll conclude into that. But before we begin, I bring my brain model with me when I give my presentations, and it's so relevant to what we're talking about, so it'll be around this weekend for anybody that wants to look at it. But it's a very complex structure. I'm showing you open, basically, we have two hemispheres. Down at the bottom is the spinal cord that transforms into the brainstem that's right above the spinal cord. And if you look at it, there's immense groups of brain cells that come together. We call them nuclei in here. And you'll see some more pictures. Just the anatomy is really astounding. So you have two hemispheres. As Ken alluded, about 86 billion. We think somewhere between 86, 100 billion. As many stars in the galaxies. The nerve cells we have, they're congregated on the outside in the brainstem, and there's what we call some deep gray matter. So all the bodies of the nerve cells are in a couple regions, and everything in the middle, what we call as white matter, is the long tracks, the connections. So you have a nerve body that has some dendrites. Actually, can you go down a couple? Just 1, 2, 3. Yeah, this is an example of sort of where you have kind of these connections up top, and then you have a long wire, and then you can make connections. You can go back to the very first slide. But that's important because if you have 100 billion neurons, as many stars in the galaxy, they have to learn how to communicate with each other. And every single nerve cell can communicate up to 10,000 of other neurons. It's really astounding what the brain manages to do, and how it does that is by connecting neural networks. So groups of neurons start to work together. And what we see on the MRI is a picture of when we are doing something. It's the whole parts of the brain, as Ken mentioned, so whether it's language or meditation or whatnot. But this is the study that I think this ashram will love. Go to the next slide. Actually, just go down one more. I'm just going to go right into it because it's really fascinating. But up top, the orange areas is what they call mind wandering. So this is also a really interesting story. That in about early 2000s, when functional MRI was first developed, they put people in the scanner and they said, just rest and don't do anything. We want to see what your brain does. And they kept seeing these areas light up, and it looked a little bit like this. It was very heavily in the midline and also connected some kind of more lateral areas. And for a while, the scientists are saying, well, we're not sure what's going on. The brain must have this spontaneous activity. You know, they're lying in there. They're not doing anything. So they, this must be just an inherent feature of the brain. And eventually what they figured out is that this was people just mind wandering. You tell people to sit and do nothing. What are they going to do? They're going to start thinking. And not only that, but the anatomy explains so perfectly. If you can go up one slide. Thank you, Anne, for, the other way. Yeah, this way. Our mind wandering connects exactly the parts of the brain that you think it would. It involves pretty much the story of yourself. It involves the frontal areas, kind of your planning to do, but involves your memory centers, which is down below. Your hippocampus is involved. Your emotional centers, that's up on the upper right, kind of this area, similar to where language is. Emotional processing has to do there. The insular cortex. And also the emotional centers are centered around the area. So essentially, this slide to me explains how and why our thoughts can jump from one subject to another subject so quickly. It's because our memory, our emotions, our frontal planning, our story of the self, not only are they so deeply connected, but they are the most active network in the brain, such that it's called the default mode network. And it came with that because they first said, well, the brain, if it's not doing anything, this is the default mode network. Later, it's mind wandering, basically. The default mode for most people is mind wandering. And go down one slide. And this is an incredible study for meditation, because this particular group basically had people punch when they caught themselves wandering. And they looked at what happened to the brain as soon as you became aware of your thoughts. And the bottom slide, mind wandering with meta-awareness, with this observation, the awareness of your thoughts, that network went quiet. Yes, question?
Did they have a focus that they were supposed to be?
Actually, for this one, no. They were just, I don't actually know. We can look into the study. For the methodology, I can pull it up. I forget what they were told to do. I think it was just, so I don't know if they were actually, thinking about something. We'll look into that. I can get you that answer. But your question reminded me of something, that did they have a focus from a neuroimaging perspective is important. Because when you analyze connectivity in the brain, they're basically choosing an area and they're looking for all these areas that are connected to their focus neuroanatomically. So just because the light up goes quiet doesn't mean the brain is not active. That doesn't happen. It just means it's not connected to the wandering mind. So basically, the mind wandering network goes quiet. This is how I teach meditation. I start with this, and then I tell people, I lead them on breathing, focus meditation, whatever we feel like doing at that time. I give them some periods of silence. When you catch themselves wandering, as everybody does, now they have a picture of it and say, just go back to your breath. You've let your wandering mind, you can let that go back to your focus, and you've quieted your network. You have to do it multiple times, and then you will start to get better control of your wandering mind network. And that's what meditation training gives us the tools to do. Before I move on, that's pretty much the crux of what I'll talk. Wait, before we move on. This is pretty big territory, language and thoughts, and this takes up a lot of use in our brain. And when we look at older neurodegenerative patients, they have plaque deposited in basically their default mode network. So one of my hypotheses is that this untrained, wandering mind, we're using our networks, all the thinking networks all the time. We're not quieting down. We're not giving the brain a chance to rest and to clear it out. So that's a little bit related to neurodegenerative diseases. But we'll go down now to the video. And I want to show, I'll find that later, but I'll come in just a second. This, by the way, a neuron, this is a robust neuron on the left, and on the right is, this is an animal model, unfortunately, which I don't like, but it is the depicting of an animal that's subjected to chronic stress, and their neurons actually retract. So when there's too much cortisol, too much stress, it also contributes to shrinking of the brain. But what I found observationally, being with people with Parkinson's patients, is that informally, if I would just say, look, let's just take a deep breath and relax a little bit, we'll get to the evaluation in a second, just that moment of helping them relax, they would move better. So that was the beginning of what I'm going to show you right now. We're going to reference that. But before I move on to that, I will say that all the teachings of yoga have largely influenced how I've approached neurological patients. So I also call this like non-attachment. When you can get rid of your thought, if you can let your thought go and let your brain relax, you're literally helping your neurons release their grip on these deeply rooted networks that you have. The first step, as Sage Patanjali wrote, is non-attachment. Once you get to this baseline, you pull back from your prior networks, that's how you can promote neuroplasticity. So that's the, yes? Yeah.
Just with chronic stress, could you talk about, what is defined the time period?
Yeah, it's an animal model, but it's, yeah, that's for like 6 weeks or so. They constrain an animal limb and they like cause that, like they can't, yeah, it's physical stress,
and
yeah.
The atrophy, is it permanent or is it temporary?
It's temporary. Yeah, it goes back. Yes, exactly. It's a very dynamic state. Yes, the brain, that the nerves will grow in proper conditions and they'll retract in improper conditions. That's also the fundamentals of brain health. So I'm going to move this over here.
Anybody have questions, please raise your hand so I can hand you the mic.
But let's see. Oh, God. Let me see if I can get, how do we, this is complex that this is set up as a separate screen. Do you see the cursor? Why am I,
Yeah, bottom right.
bottom right, thank you. It doesn't help that. Okay, can we move this guy back? Yeah. We're just going to close that. Good. Yeah.
It sounds like you're making, are you intending to be making
Mm-hmm. Let's see. Now, okay, we're up here. Now we need to get the cursor back. I might need, let's see. Now, is this, oh, here it is. Okay, we're good, yeah. Okay.
I'm
what is your
curious to know
question?
what the statement is that you're intending to be making,
Yeah.
or if you're intending to draw any conclusion at all
Yeah.
about meditation and either the formation of plaque in terms of Alzheimer's. And so actually I have an uncle who has Alzheimer's who is a longtime monk.
Okay.
And with Siddha Yoga with Guru Mai.
Mm.
And then my father-in-law had, and my father's wife both have Parkinson's, and my father-in-law is a longtime meditator. And it seems hard to, it's easy to ask questions about just what, it's easy to, I would say that with my father-in-law, certainly his ability to deal with the very difficult situation of having Parkinson's was improved by meditation. But it would be hard to make a connection that the meditation actually made much of a difference in terms of slowing the disease. And similarly with my uncle who's a monk, that and Alzheimer's is like, it's a nasty disease. It's and a lifetime as a monk meditating didn't make it not happen.
Yeah. I can answer what I know from many different studies that have been published. First is one, I'm going to say in kind of no order. I'll come back to answer your question. But It was by all means a hypothesis and an assumption, but we do see that the location of plaques tends to line up with default mode network. And if we know that default mode network is mind wandering, it naturally should lead us to at least investigate whether meditation can reduce that. So this is so far where we've come with the science that's been done. One pilot study for people with mild cognitive impairment, meaning early signs of memory loss, showed not only for the 8-week MBSR training, that's what John Kabat-Zinn developed, that's that big graph there. So standardized training that they went through. Their memory improved, and they actually had increased volume of their hippocampus, which is a super cool study. So with people with Alzheimer's, their memory centers shrink. And they have altered connectivity to default mode network. So this 8-week pilot study of a very small handful of people showed statistical difference between the control group and the people who underwent the training. The control group continued to have very slight diminishment in their hippocampal areas, and the intervention not only stabilized, but several individuals, just by undergoing an 8-week training, increased the size of their hippocampus. That's one. Two, did you want to say something? Go ahead.
I wanted to ask a question, which
Yeah.
is, I mean, how do you determine what is, so also you're talking about a study, and we know that something studied, something observed, behaves differently from something not. So how do you determine? So I also know doctors who've done research on the heart, and just the fact of being observed, of talking to somebody about what is happening, of having somebody come and take measurements, that changes
physics. But yeah, exactly. But for this is looking at volume, and that would not change. That we don't think changes as minute to minute, because this is looking at the volume of brain structure. So brain activity, metabolism, connectivity can change moment by moment, and would indeed change by being observed. Like aware of thoughts, change your thoughts. That's a moment to moment. That's the functional MRI. The volume that I'm talking about was just take a snapshot of the brain like this. Take one picture under it, and if I chip a piece away, take a look at it. You'd see in the photograph like a physical change. So that we think is a physical change. That takes a lot longer to change. But a more recent study in Nature, this is really cool. They studied coherent breathing, which is a breathing exercise to stimulate, and they had the hypothesis that people are in adrenaline mode too much, and our genes show that we have too much epigenetic signaling for this stimulated state. And coherent breathing, which is a breathing exercise, is 5-second inhale, 5-second exhale. You can do it through bells. They compared young adults and older adults. They looked at their genes, and they looked at plaque deposition, and the group that underwent I think it was 4 weeks of 20 minutes once a day, but they had the option to do it twice a day if they wanted to. Their genes changed towards the parasympathetic mode, and they had improved clearance of beta amyloid and tau from in their serum, which again they make the connection that this is indicative of the brain clearing it better. So I'm putting two and two, putting many different studies together, but we are having some signs that people with cognitive impairment can learn to meditate. It can change the deposition in their brain. It can change their functional connectivity. It can change the size of their brain. They have the capacity to learn it. But we need now, larger studies. But I will say that there's an extremely interesting observation that I've made with my Parkinson's patients, that just sitting and meditating does not always have the outcome that we want. And we need better markers to actually guide people to having the physiological changes that we want to see. So just because someone is a monk and lives in an ashram, I cannot say that they are suppressing their default mode network or living in a parasympathetic state, which I say as what I have found to be very therapeutic for the brain, and that's what I'm going to show you right here. Does that sound good? Does that help answer some of your questions?
Yeah, no.
Yeah, okay.
You can go.
I think we can also, let me just make one remark too, that
Yeah.
you mentioned that you're asking about the effects of, like, on one person. We don't know what he would have been like without his meditation. That's
That's right.
one. And two,
Yeah.
the basic scientific method, when you talk about observing and that changing thing, is we always have a control group that also gets observed and also gets trained. So if you do an experiment that's well done, then there's only one difference between them. And so we can make a little more of a stronger inference, but it's always not going to account for every single subject. So anyway, sorry. I think we, just to stay on time, I want to hear all of them. Yeah. Let's get through this and through the setup, and then we can open this up, and I'd love to take the question.
Okay. Is the sound set up, actually?
Are we set for the sound?
We're going to do the sound, and then I want to just explain the video to guide you to what you're looking for. Parkinson's disease, they have movement difficulties. So some people are hunched over, they may have shuffling gait, they may have, not smooth gait, small steps. They also have something called bradykinesia, which is, we always test this in the neurology clinic, how their fingers are moving, and they lose the ability to move smoothly, fairly commonly, most people with Parkinson's. So what you're gonna see in this video is a gentleman. This is actually the first time I met him, and I said, tell me something that is challenging for you. And he pulled this up, he says, well, I've noticed that every time I move my left hand, my right hand starts to tremor, and it's bothering him because that's his universal hand. So that is what he's telling me in the beginning. Hit play.
I can't do it. Okay. It makes me tremor
Okay.
to even try. But if I stop doing that, that's all.
So now we've done some breathing exercises, and we have retrained the right hand to move mindfully and increase the speed just a little bit. Keep going. Very good. Good.
Thank you. So
5 words.
Oh, let's turn off the sound now. Okay, good. I always forget to stop. All right, I'm gonna leave this. So this is I'm gonna conclude now in just one sentence for the interest of time. But basically, what I teach first of all is physiological relaxation, and that's what I call the non-attachment. Because when they calm down and also let go of their thoughts, they're in a place to start retraining their movement. So that's the gist of sort of the work that I'm doing. Related back to Sanskrit, because that's what this is about, and thank you for giving the time to share all this in this precious time. I want to add, for Ken's last slide, one thing that may be unique about Sanskrit is the vibration of the language, which I think is different than, say, Finnish, and there is a study that I'll pull for you that's looking at vibration. We have found that sound healing, just instrumental work, also can transform the body for Parkinson's. So lots of relations to all sorts of Eastern traditions that we're investigating. So thank you very much, and I'll be around this afternoon for final questions.
Thank you, Sarah.
Yeah.
All day, and thank you so much. We will now, Nabin will give you a presentation of the technology, and then we'll start setting up for the demo and thinking about the experiment. But I really want to encourage, we should get into a discussion, we should get into a debate. So let's finish the last presentation, and then research scientist now at the Yale School of Medicine and Haskins Laboratories Group. He did his PhD in Germany. His background is both engineering and neuroscience, incredible work. And to my good fortune, we've begun collaborating on several projects in our lab. He is really doing, I just have to say one thing, he's doing extraordinarily innovative approaches to looking at brain data and making sense of complex populations. So welcome, Nabin.
Thanks, Ken, but it looks like I'm doing a lot of important work but can't fix a display here for the presentation. So
Wait,
let me try.
Okay.
I could just mirror the display. Okay, I think that's okay.
So while you're waiting, one thing to think about is with a device that can monitor the changes in brain as people do different tasks, what might be an interesting thing for us to look at now that we have it here this week? Just something simple, but maybe something with chanting or something with meditation. We should discuss.
Do you
Go
have
ahead.
the pointer?
Oh yeah, where did I put that? Oh, there it is.
Oh, there we go.
Here it is.
Okay, so hi everyone. I don't think this would be as interesting as the previous talks because this is the boring bit of all the things they said, the technicality, right? So how do we do all the things that they just talked about? Like they showed you nice pictures of MRI and different lights here and there. So what I'm going to talk about is how do you get like these kind of pictures? Or how do you do these experiments? What's underlying behind the scenes, right? So and I think this is important from my perspective because I'm an engineer and I like those technicalities, but also it's useful to understand for everyone that what lies behind that so that we could design and when you come up with different types of questions, it's important to know what we have available, right? So and this picture is, by the way, the winning picture of the brain art, which NIH organizes every year, and this picture won the best brain art award in 2022. So it's a beautiful brain. They actually kneaded it with, so these are the wools, and these are like actual clothes. So it's a 3D model what they built in. So it's really cool. Okay, so yeah, I put these slides just to introduce myself. So I'm Nabin. I actually originally come from Nepal, Kathmandu. And when I say Nepal, people imagine that I run away in mountains and then there were only snows. But I actually grew up somewhere like this in a city where there are only temples, and this was one of my favorite hangout place for a long time ago. But so I did my engineering undergrad there, and I moved to Mainz, Germany for doing my graduate studies, and that's where I started the neuroscience. And it was funny because the incident why I got interested in neuroscience is like kind of this kind of seminar. So there was one workshop in the university where the brain-computer interface was pretty new back then. And then they came to our university and they wanted to display us what you could do actually with that. And they asked for some volunteers to sit down, like what we would do afterwards, like put on the cab and then do the stuff. And so I volunteered and they put on the cab and it's like, okay, think about a few letters that you want to write to someone, and words. And I was just thinking there, sitting, and then I could actually see it being typed, and I could send a text just by thinking it, right? And that was like, wow, okay, so I need to know this. And that's when I talked to my professor who was doing this, and that's where I started learning about the signal processing in the brain, or biomedical signal processing, and I switched to neuroscience and did my PhD there. And that's where I all learned about like different techniques of neuroimaging. So this is one example where we are doing the EEG and the transcranial magnetic stimulation in a patient. So she is an MS patient, and this was our lab there. And this is one of the Parkinson's disease patients. And he is having what we call the deep brain stimulation. So the 2 electrodes are implanted in his brain, and the cable coming out is actually from those implantation. And then we were actually looking into how those recordings differ and based on different tasks. And there I learned about the magnetic resonance imaging, the MRI, which will be the bulk of my talk, because this is one of the basis of neuroimaging. How we get the picture of the brain is by using this machine. And yeah, so this is where I learned all the things. And now going to the neuroimaging part, I stole a slide from Ken's talk, where he gave a brief definition of neuroimaging. Right? So what's neuroimaging, or brain imaging, so to say? is just an umbrella term which tells us different varieties of methods which can directly or indirectly, or we could say invasively or non-invasively, image different structure as well as the function of the brain. And this technique is not only helpful in revealing different brain anatomies, but it also is very helpful in revealing different brain functions. And the newer approaches that we have now here, which has been developed in the last 5-10 years, they are really good in identifying the split-second timings, right? So you could pinpoint what exactly happened when and where, right? So this is very important with the newer technology, which was not possible, let's say, 30 years ago or 20 years ago. So, so talking about the techniques, what is available out there, there are many of them. And then you could see the development, right? So this is the picture in 1988 about all the techniques that were available. And these are the techniques that is available in 2014. So you could see the number of development that goes on. And what you could see is that there is always two things that are important when you look into the brain. One is to find out what is happening, or when is happening, and where is happening, or three things, sorry. So what you see here in the x-axis is when it is happening. Is it in the millisecond range, second range, minute, hours, days, and volumes? And what Sarah was answering before was, for example, the brain volume, it doesn't change in milliseconds and second range. So it only changes over days or months, right? So it's not possible that a sudden observation might have changed that. And on the y-axis is the resolution, like in what level you could see that. For example, we could map different. So what Ken showed before, saying that we could see the brain activation in this area and that area are these areas. Now, if we want to go down to the neuron levels or the synapses level, saying that, okay, which synapses are actually firing now? Unfortunately, we can't do it in humans because you have to open up the brain and take the brain out, and so it's not possible. But it's definitely possible to do it in animal models. And this has been done, and we could get really synaptic level information in the millisecond range by using these techniques. Right? Okay, so actually to talk about the brain function and knowing about it, and the history is pretty long. And it's when I said that the advancement where we could actually look into the split seconds and finding the function of the brain is pretty new. The idea was really old. I mean, so I think it was in 1865 when an Italian professor, he wanted to observe that how can you know which part of the brain is functioning. So he came up with a very brutal way of looking into it. So what he did was he drilled a hole in his skull, and then he observed that the brain was pulsating with a heartbeat, right? So and he observed that, okay, so this is interesting, the brain also has a pulsation. And he made few of the holes, and depending upon the kind of function the person was performing, they could see that the pulsation increases, decrease. So he came to the conclusion saying that, okay, so the brain function in any area would lead to the increase in pulsation, or so to say, the blood flow, right? And that's fascinating. Even though it was a brutal way of doing it, that's still true today. The technology that we are using is based on exactly the same principle, where we look into the blood flow in that region when there is a brain function, right? And it has been developed over several years, and you could see that there has been 4 Nobel Prizes in these timelines for these developments. So you could, it has took a long time so that we get here and we could see what we could see. Okay, so now a little bit about the MRI scanner, because this is the device or the machine that is actually used to image the brain. So what is this? I don't know how many any of you have seen scanners, MRI scanner? Have you? So how many of you have been there or inside? Oh wow, a lot of them. Okay, that's interesting. Okay, so those who haven't seen it or have been inside there, so you normally lie down here and your head is somewhere here, and you put a so-called a channel, a head coil, and then you are rolled through this small bore, and then you lie down there without moving for 15, 20, half an hour, depending upon what you do, and then they capture the picture of your brain, right? And it's a very huge machine, so it's like, it weighs around 17,000 pounds, and for those who have still the European brain, it's like 7,500 kilos, right? And it can, and it's a, it's a very powerful device in a sense that it could create a perspective, because I was lucky to see this, because you don't see this every day, because when you want to install an MRI, you always have to do it in a basement, right? That's the lowest you could go, and you have to do it before you build something on top, because you have to bring that in and then build the whole house or the building, right? So this was being so this is the scanner. When I was in Germany, they brought a new scanner and wanted to put it in the basement and then build a new building on top of that. And this is where you could actually see inside. Otherwise, you could never see something like this. And for those fun facts who don't know, is even though this is a magnetic scanner, there is no actual real magnet inside. It's just the miles and miles of coils. And that's generated by electromagnetic principle that we all know. When you pass a current through the coil, it generates a magnet. So there are like at least 2,600 miles of cables that has been turned there, just inside here to generate the magnet, right? And you can imagine, and this is, I'm talking about 3 Tesla. And now we have up to 9.4 Tesla being tested in humans already. So you could imagine the complexity of this thing. And it's very costly to operate, because when you generate this much magnet, the coil gets heated really fast. And to cool it down, what you need is helium, the liquid helium. And that's very costly to maintain. So the most of the cost that's gone, or that goes for running a scanner, is those heliums, right? So every time you need to run that. Okay, and from the types of MRI, that machine could produce a lot of different types of MRI, right? I will not go into detail of any of these, but I just wanted to show you these just to give you an idea of what are the types of images we could get out. It's just not this one, the black and white, what we saw. I mean, it could generate so many different types of images based on what you're looking into. Are you looking into different barriers between the neurons? Are you looking into the different magnetic inclusions between, or the molecular interactions? Based on what our interest is, you could generate different types of image by switching what we call acquisition paradigm, right? So you plug in different acquisition paradigms and you could get different types of images. I'll not talk about all of these types of images, but I'll talk some of these, some of the interesting ones, or some of the most common ones. And one of them is what we call the anatomical imaging, or just to look into the anatomy of your brain. And what you are seeing here in the video, which is being played, is the highest resolution anatomical brain image exists ever, right? So this was released 2019, and this was obtained by a very difficult process. It was obtained in a 7 Tesla scanner in Harvard University. And what they did was, so this brain was actually donated by a 55-year-old woman who died of no neurological disorders. So they took her brain out and they scanned this in 7 Tesla scanner for 5 days continuously to get this 100 micron resolution brain image. And then this is one of the benchmark now to show that this is how exactly the brain looks like. Right? So you could really look into the intricate details of each regions in the brain. So this is fascinating. This has changed the field in a significant way. And the anatomical imaging, there are different types of anatomical imaging, and it's always important to acquire a right data, right? For example, Sarah can say a lot about this. She's a neurologist, and she probably looks into these images every day. But for example, based on what you want to look into the brain, you can obtain different types of anatomical images. Here is an example of a patient who has tumor, right? So if you want to look into, okay, where exactly is the tumor, then you would do something called T1 weighted with contrast, right? That's a name of the sequence. But if you're interested in looking into what we call edema, or the swelling that's outside the tumor, which is the water, which is just outside there, then you would need something called T2 weighted scanning, right? So that means based on the question, or based on the clinical interest, you would need different kind of clinical sequence, even though it all falls into the anatomical imaging. So there is a different layers of complexity when you go down in choosing the right sequence. And now I move on to the different kind of imaging, diffusion imaging. And why I want to talk about this is, one is that you should know about this, otherwise you are left behind. I mean, look at this. It's everywhere, right? I mean, it's an advertisement of Nike shoes, football boots. So they claim that if you wear these boots, it will enhance your white matter, right? And I mean, you could play football better. I don't know. So it was the album cover of, anybody listens to Muse? You do? Okay, yeah. So it was the album cover of the Muse, an alternative rock band, I guess. But it's funny because I like that they chose the diffusion imaging, being a neuroscientist, but I didn't like the album name because it's the second law. And the second law is from the second law of thermodynamics, which has nothing to do with the diffusion, right? So, but they try to fuse it together and then somehow make it cool. I mean, yeah, if you're a musician, I guess you could do anything, right? And even these days you could buy a T-shirt, and then you could see people walking around with these kind of T-shirts, okay? But the whole idea of this imaging is not about creating these beautiful pictures, but actually doing something like this. So what is this? This is my brain, and this is the white matter tracks of my brain when I reconstruct it. So what you could do by using this imaging is you could track all the white matters in your brain, and you could see, based on the colors, different directions where it is growing, right? So the green is going from one hemisphere to the other one, the red is going from the top to bottom, and the blue from side to side, and so on, right? And this was, this picture I used because I generated it by myself, and I used in my PhD defense, and one of the committee member, he liked it so much that he actually used it in his book cover. It was really nice, and he sent me the book here. I was really happy to find that. Anyways, so let's move on the other interesting part of it, the functional imaging, which Ken and Sarah talked about a lot, right? What we see when we talk, when we read, when we chant, when we meditate, and all of this. So these all falls in the functional imaging. So when I talk about anatomy, you just know what's in the brain, right? But when I talk about the function of the brain, you would know what exactly do you want? Do you want donuts? You want beer? You want to sleep? Yeah, right? So this is what's the difference between an MRI and an fMRI, right? Or the functional MRI. Or if someday we will get there, we could just have an fMRI installed in an airport, and we could just see that who is going on a plane with the bad intentions, right? I mean, it's possible. It's definitely possible. So now, let's look into what it exactly does, or what's the use of these techniques, right? So one of the most fundamental use of this which has been done for many years, is finding the reasons which is associated with a specific function, right? So you could see that over the years we know specifically like which area is related to visual or outcomes, right? For example, what Ken showed before, that every time you see something, eyes closed and eyes open, there is a region in the occipital lobe which gets activated. So it's been true all the years, and it will be true for many years, right? So that means we know that all of these brain functions are being associated with different areas in the brain. And even more so, recently what we know is that it's not only one brain region which is specific to one brain or one function, it's the network of regions. So now we talk about functional networks rather than functional regions, or the ROIs of the brain. So we know that when you do one specific thing, there are different regions of the brain that gets activated at the time, right? And that's what we call the functional networks. Now, the next question is, how do we know this, or how do we get to this, right? And this is what we call, by using a technique. I'll not go into too much detail, but I just wanted to give you a slight overview of the theory behind it. The idea how we get to this is by using the term called BOLD signal, or the blood oxygenation level dependent signal, which was termed, developed by this brilliant scientist, C.G. Ogawa from Japan. And when you think about this, all the neural activity in our brain needs energy, right? It needs some form of energy to do that. And it's amazing because it needs so much energy you can't believe. It consumes 25% of the glucose intake for your whole body, and it consumes about 20% of the oxygen that you consume. But surprisingly, it just weighs 2% of your body weight, right? So that small part of your whole body consumes this much energy. And what's even more surprising for me is that there is no energy storage capacity in the brain. It's just always just-in-time delivery. I'm hungry, there we go, here's a pizza. The drone flies into the door and they bring you, right? So it's exactly the same system in the brain. So it cannot store any energy for itself. It just wants that, okay, I need an energy to function, do this thing in this part of the brain, and it needs to be delivered there as fast as it can, right? And that's the brilliance of this. And so how does it work is that, so there are like a whole network of blood vessels that's covering our brain. And these blood vessels are responsible for exactly doing this. When the brain functions, when there is a neural activity in a specific region of the brain, it tells that, okay, I need some energy there, and then the blood oxygen flows there, and there we have higher blood oxygenated level in there, and what we call, by a process of neurovascular coupling, I'll not go into detail of that, we will get what we call the BOLD signal, right? So what we are interested in knowing is that to know how to measure this signal, right? We know that we are getting the more oxygenated blood in a specific area, and what we could see is that this looks something like this. For example, if you would see a picture of a macaque, like here, Naruto. How many of you know Naruto, by the way? You know? Yeah, that's cool. So for those who don't know, he is a very famous macaque because this picture was actually his selfie. He took himself. And it was subject to a long lawsuit, right? Where the photographer claimed that the copyright belongs to him, but the animal rights people, they claim that the photo actually belongs to him because he took the photo himself, right? And as far as 2014, the macaque is winning. So the Wikimedia hasn't put down this photo yet, even though the photographer have claimed the copyright. So it's actually his photo. So you're free to use his photo until and unless he allows you to do it, right? So what happens when you see a Naruto in your brain is something like this, right? So what happens is your blood oxygen level goes up within like 4 seconds, and it reaches the peak, and it goes down in about 5 seconds, right? So this is exactly what we know. So when I talk about all these blood vessels giving the oxygen, when you can measure those signals, you could actually find out that where exactly you are seeing the stimulus, right? When I see these pics, I exactly know that, okay, here you are seeing a Naruto, here you're seeing a Naruto, here you're seeing a Naruto, and all of these. So that's the basic principle of functional imaging. By looking into these BOLD responses, what we call, or the oxygen level, we will exactly know what you are doing. And when you reverse engineer that, then you could find out the brain functions, what's going on, just by looking into the oxygenation of the blood vessels. Okay, so now let's move on to a technique called functional and near-infrared spectroscopy, which is here on the table, right? And why this is important? I mean, I talked a lot about getting this functional image, but the device I showed you was 7,500 kilos or 17,000 pounds, huge machine which needs a very high cost, which needs to run in a liquid helium and needs to be put in the basement. And most importantly, when they have to get the image of you doing a certain function, you have to lie there without moving. The one thing all the experimenters tell you is do not move. Do not move your head, right? So we need something where we could still capture the BOLD signal or the BOLD response or the function of the brain, but where you could move. For example, you could be dancing, right? I mean, and you want to know that, okay, how is my brain functioning when you are dancing? You could be learning about baby trying to respond for different things, like what happens in the brain when a baby is doing something, or what happens when they are socializing with some other person or their mother, how it is different in terms of different interactions. And all of these activity, or for example, doing yoga, and my favorite is this one. The researchers, I guess in Germany, they did this study where they looked into the brain function and how it differs when you miss a penalty in a soccer game between the professional footballers and the amateur ones, right? I mean, and they wanted to look into that because the question actually is interesting because what they came up is that, is it the case that more professional you become, that more pressure you have scoring the goal, right? And it turned out to be true because you see much more activation in the frontal lobe when you're a professional footballer and miss the penalty. But if you're an amateur, it's like, yeah, I mean, sure. I mean, it doesn't always go in there, right? So, so you could do all of these things by using this technology, what we have, and what we call the functional near-red spectroscopy. And just to give you an idea or the background of how exactly it is done, is it uses something called near-infrared light. So there is a huge range of light. There is a visible range, there is an X-ray, there's an UV range, and so on and so forth, and then infrared. And what we use is a range which is very near to the infrared. This is between 700 nanometer to 900 nanometer. And why we specifically use this range is because below 900 nanometers, the light is observed by the biological tissues, right? And above 900 meters, the light is observed by water. So you could see the yellow peak here. So if you go outside of 900, it starts getting peaked. That means you will not get anything out of it because if everything gets absorbed, you will not get a signal back to build some images. So between this range, it's really fascinating because this is the range where the light is absorbed exactly in the right amount and differentially for oxygenated and deoxygenated blood levels, right? So that means the oxygenated blood levels absorbs this light at the peak around 850 to 860 nanometers, and the deoxygenated blood, it absorbs around 760 nanometers. So that means by throwing these lights in, which we do something like this, so there are like different optodes that we put in the top of the head here, and when you send a light source from here, what we call source, and there is something called a detector here, it will detect the light which is attenuated through a specific brain region, right? And what we know is that this attenuation is different if the blood is oxygenated or not oxygenated, right? And then what we know from previous slides that if there is a brain function, there is a more oxygenated blood. That means if you see that there is a more observation or absorption of this 850 nanometers, then you know that, okay, there is more oxygenated blood. That means there is some function going on in the brain. So this is the basic principle of how we can quantify where the brain function is going on. And this is exactly what I have it here. And these are the optodes that would be put in the scalp, which you see here. And the blue and the red ones are the sources and detectors. And we will try this soon to in somebody's head, hopefully, if somebody's willing to. And finally, I just wanted to show you a couple of examples because we have a lot of these examples already before. But by using this technique, what we have, so this is a study from a colleague of ours at Yale, and what she has done is a really interesting study. What Ken talked about very shortly about the entrainment, right? So how the brain rhythm syncs between two persons when they are just doing the eye gaze. They are not talking to each other, just sitting there doing the eye gaze, and how that differs between if you know that person, how related you are to that person, if there is a stranger, if you're talking to a robot, if there is a 2D images. It has been shown in so many different conditions how the brain rhythms sync just by the eye gaze, right? And that's fascinating. And you could do this, and you will never be able to do this in an fMRI, right? I mean, how do you put two fMRI people eye gazing to each other, right? So, and the other interesting study, which is also done in our lab by a famous neurodevelopmental researcher, Dick Aslin, is what he showed was, and this is one of the interesting studies. So you could see that a small kid here who's been wearing the cap, and what he showed was when you look into the brain at 6 months, that was able to predict the language development at 12 and 18 months, right? So this could give you a really important information about the environmental interactions that you need to be doing to infants at the age of 6 months, even though you feel that they are not learning any language there. But this study was able to show that it's very, very clear that this was very predictive of the outcomes, the language outcomes at 12 and 18 months, right? So, and this study, why it is important with the FNIRS is because this is impossible with an fMRI, because now this kid is sitting on a lap of his or her mom, right? And this is not possible in a scanner where you have to lie down the kid and put the head cap. So this is interesting. So this technique in general is interesting for doing these kind of studies. And what we want to know about is that your interest now. So I give you like a whole background of what you could do with these machines. So if you have this power to do whatever you want to do, what kind of questions would you want to answer? Which is interesting for this community, which I'm saying in a perspective of doing a lot of meditations, doing Sanskrit chanting, being an expert in Sanskrit, what kind of questions would be really relevant and interesting for you? So this is, I think, what we would want to open a discussion with, and I think Ken also wants to join.
So
Yeah.
okay.
Okay.
First of all, thank you, Nabin.
Thank you.
So, as Nabin was saying, first of all, I want to make sure that we are able to. It's not working. Make sure that we're able to take questions. Again, we have basically another hour, and then we have dinner. And we want to start to get people and demo. I think we're going to show them what the signal looks like when you do different things. But as Nabin is saying here, our thought was, given everything you've heard, and I know it's a lot, and the things we're talking about for Sanskrit, like the importance of sound, of chanting, the importance of repetition, the importance of understanding the meaning, or the importance of quieting the mind, the importance of learning the writing system, any of those things. This device that we have, that Nabin just showed you all those pictures of, and we're using this in a study together with children, we can do. We won't be able to complete an experiment, but as we get set up and maybe demonstrate what the signal looks like, and Nabin did an amazing job of explaining the physics, and Sarah on how this is important for neurology. We can also discuss questions as we're doing this, but let me begin. Given everything you've heard, what would be an interesting question if we put the cap on? Go ahead. And then we'll take Indira.
There are so many interesting questions.
Yeah.
But one, I have two that come to mind. One would be something about also like reactions to pain, just like sort of similar to our work with Parkinson's people.
Yeah. Okay. Come.
Reactions to to discomfort or something like that. When before or after chanting or meditation. And then the other question is, so I'm sure you're all familiar with like Jill Bolt Taylor's work on, she wrote this book, My Stroke of Insight, where the left brain shut down, and the right brain, she had this powerful experience of oneness when the left brain shut down. I don't know how you would test this, but perhaps like activity in that part of the brain after like chanting or meditation or something like that, the difference between like
those are both great ideas. And even in terms of the pain, there's a study that came out recently from our colleagues in Wisconsin where they looked at long-term meditators and novices, and they were going to give them heat, which is pain to your arm. And they were preceding it with a little signal, so that you do like Pavlov's dog, you learn that when the signal comes, you're going to get pain. And what they found is that the people who are experienced meditators, they don't react to the signal, and they also relax the brain activity much quicker after the painful event, really showing how meditation is affecting the attention systems. So that, but that's a great set of ideas. One of them is, does doing the chanting change what your state is from before and after? We very often do that in our lab where we look at pre-something brain activity and then something, like a treatment or a chanting or meditation, and then post. And we can certainly do that. Indira, you raised your hand. What was your thought?
I think we have just this precious hour,
Mm-hmm.
and I think we should apply it to the work we do here.
Mm-hmm.
And I would suggest possibly, what does it look like when someone listens to chanting as opposed to when someone chants themselves?
Mm-hmm.
But something with chanting, I think, is what we should do, because that's what our guru gave us. He gave
Sure.
us chanting as a...
I kind of
Jewel.
anticipated that you might. So now, as we were talking before, go ahead.
I'm just
And-
taking
Just
notes
to
just to
follow
make
up
sure
on
that I
that-
don't forget what you
Yeah,
guys
follow
said.
up on that question. Like,
Yeah.
I just want to add. So my dad has been chanting for 40 years, and
Mhm.
he's Hindu, and he is very much about chant loudly. Don't chant in your mind. You know. So
Right.
I don't know whether speaking out the words is different.
Chanting
from that.
aloud, yes. In fact, when we do studies of people reading or talking versus imagining talking, they're very similar, but there's a whole lot more activity, important increases when people actually produce the signal. So we would definitely do that. Go ahead, as we set up. And then I think, Indira, you're right, we can do something. We have to make sure it's analyzable, that it's a design that you can infer something. We'll talk about that. But let's get all the ideas on the table. Go ahead.
I just want to throw this out before I forget it.
Yeah.
And I was curious, have you used this design or this experiment with schizophrenic patients? In the sense, is there some way that, you know, by eye gazing and using this, one can, because I'm sorry, my background is in integrative medicine, and I specialize in Ayurveda, and we work with natural
yes,
medicine.
of course.
So I often wonder if there's a way that when they do these exercises with me, I can give them a signal to, you know, calm some of these noise factors that go in the brain that
Absolutely.
confuses reality, and impose what I think is the right way to at least show them single.
Exactly. What is your name?
Sangeeta.
Sangeeta. So actually, and I think, Sarah, you might want to weigh in on the schizophrenia and brain, but I will tell you that there's a great deal of, there's a fair amount of research on schizophrenia and brain patterning, of course. And in all of our research, what we do is we try to create some sort of learning experience, some sort of context where my work is not in schizophrenia. I don't think you've done work in there, but we work with similar questions in other populations. And what we're looking at is whether or not the brain can give us a clue. Sometimes they can't tell us, but the brain can tell us that we're on the right track. That's why we use it with children, to see what kinds of learning experiences different types of children will benefit from long before they can ever tell us about it. And so in the same way, in the work on schizophrenia and the work on with, thought disorders in general, as well as the work on much more frequent studies on anxiety and depression, which is quite a bit. People are looking at using the brain imaging to see whether what they're doing is working. And that is exactly what you're proposing. And that's pretty common for us. Scott, go ahead. Oh, sorry. Okay, I think it's Andrea and then Scott. No, go ahead. And we're setting up, and then we'll, as Indira said, I think we'll end up chanting in this, but let's take a look at that. Go ahead.
I have them.
Andrea.
I would have been totally happy to wait, but my question would be something about the role of understanding the meaning of language in
Yep.
the chanting. Like, does the brain look different when you know what the words mean?
Exactly. So there's I'm sorry, I can't resist. So there's a beautiful study, and we've done some of these, but there's one where they looked at two people, two brain patterns, and remember I mentioned and Nabin mentioned about rhythmic entrainment, that the brains come together, and they had it in two conditions in the study out of Princeton. One where you understood the story that the person's telling, the other one where it's in a foreign language. And when you understood the meaning, the entrainment, the connection with the storyteller was, this is the Hassan et al. Papers, And very much along the lines of what you're saying. When you're learning this language, Sanskrit, where does meaning come in on top of grammar, on top of phonetics? And yes, it will, I can tell you from having done this kind of work, that it will increase many of the different important networks. The question, though, is if we're asking, like, what's the best way to learn, can we find that the use of combinations of meaning and chanting and other things work better in some cases than others? That's where the sensitivity, what I always say to people is that the brain imaging, as I use it, as we use it, is exquisitely sensitive to individual differences, to what's happening inside the brain. And it's useful in asking what might be the best approach to different kinds of learning. But meaning has a very different pattern of activity, not surprisingly, than when you just know the sound patterns.
But if you know the meaning, are you giving up something that you're receiving on the sound, on the level of the sound?
Well, you
patterns?
sound like a yogi now. So nobody would ask that question in neuroscience. They'd say, like, it's either meaning or it's nothing. In terms of, that's a great question. Basically, what you're asking is if the immersion in meaning and concept is taking away some part of the experience that is deeper.
Yeah.
Nobody would ask that question in my world or his world or her world. No, your world they might. Go ahead, Sarah.
I mean, I think you could take,
Could easily do that study, yes.
That's what I was thinking, though. If you have, you need to check that somebody you need to design in terms of somebody who has no experience with Sanskrit listens to one of the slokas versus somebody who has experience with Sanskrit listens to sloka, and then you need to just, I would say at least 2 comparisons, but then you run to see another Sanskrit sloka that you don't know the meaning of, but then another foreign language. So you can keep running, I would say, different experiments, and you can sort of get some signal in that.
Yeah.
But sound vibration of the chanting, that's what I was thinking. Listen to something in Finnish versus Sanskrit, and how a completely novice person, how their brain would react differently.
No, but that's great. But it's interesting because in neurolinguistics, the only question people ask is, what do you get when you add meaning? Because you get a lot. But nobody asks what happens if you subtract this. It's very interesting. Go ahead, Scott. I think you were next. And we're just setting up, and again, I'm mindful of the time. We're most likely going to be putting it on 1 or 2 heads now, and then we'll show you the signal, and we can think a little bit. And one possibility we could think about, if it doesn't interfere, is if we kind of brainstorm a little bit on what we'd like to see, then either over the next day, if things work with the recharging, we might be able to have people come up to the music center and help give us the data on our own experiment. It won't happen in the next hour, and I went on a long time. So, but we will be able to get started, and then we can maybe actually collect some data this weekend. Sorry, Scott, go ahead.
So one of them was similar to what was just spoken about, the aspect of just the vibration versus the emotional component. When you have a vibration plus an emotion behind the vibration, let's say a Ganesh mantra that you know, or whatever you're chanting versus maybe just the Sanskrit alphabet.
Right.
And you don't even know anything about Sanskrit, and and then the other one that comes to my mind is going into exalted states of meditation, and everybody wants a shortcut to get there. At least at this point, I think after a lifetime of meditating, you'd like to figure out ways of going deeper, more profound ways of going deeper.
Exactly.
And I'm sure there's got to be tons of studies on these masters. And so the question to me is somehow linking between these exalted states and whatever technique we're doing to try to activate.
Exactly. And in fact, what we could do, Scott, that's a great point. What we could do, for example, is maybe even on another weekend come back, or even up in our lab, and do some of these studies that you're putting together. We can always find people to sit and do them. But here we have expert meditators. Let me just say one thing about what you're talking about. There is a lot of research, especially out of Wisconsin, on monks who have 100,000 hours of meditation versus novices and intermediate, and it's very interesting. I'd be happy to share some of that. But there's one guy in NYU, Zoran.
Zoran. Yeah, it's a
Yeah.
difficult last name.
And
but
this guy's got real moxie because it's very hard to imagine how you could image samadhi or how you could image what he calls non-dual awareness. He's a Buddhist, but he did. And it's very interesting. You know, it doesn't tell you what it means to be non-dual, and never will. Just like knowing the wiring diagram of the brain, when I like a pink umbrella, it doesn't tell me what it means to like that. But it does tell you something about how you get there, maybe about how you can induce it. His work is amazing, showing this this actual.
It would be nice to monitor stress hormones at the same time.
We do that. That's exactly.
And then to see if there's any long-standing benefit.
Exactly, and that's where the research is, Scott. Exactly there. Go ahead, Shanta. And we're almost set, I think.
Yeah.
Wondering about the intention of, say we're doing chanting. My intention to think about what is the intention of the chanting.
Right.
Am I intending to get dinner faster by chanting? Or am I intending to
Exactly.
have the mind become more restful due to this chanting? I'm wondering if intention has anything to do with it.
Yeah.
Or can.
It must. That's a great question, a great point.
I
Go
love
ahead,
that.
Margaret.
Oh, sorry. I love that. Actually, we kind of think alike. I was actually thinking about it in terms of independent variables and dependent variables.
Yeah, of
so
course.
4 independent variables just for us to think about. One is chanting, but focus on it. So to your point, with the strong intention.
Right.
Secondly, most of us multitask, meaning we check our emails, look at our phones, listening to presentations, etc.
Right.
Second scenario, independent variable, chanting, but while checking email or checking the phone.
I love it. Yeah,
right?
it's great.
Bring it into the modern world.
Yeah.
Thirdly, because we are in a room full of meditators,
Yes.
what if we're chanting from the third eye place quietly? So for strong meditators, we silence that chanting, but the vibration, in theory, should be a separate, right? Independent
of
vibration,
course.
right?
Yeah.
Thirdly, the fourth will be singing to the same sound in an L2 language, but non-sign Sanskrit.
Yeah.
Because it talks about the earlier point
That's
of
right.
there is something different, Sanskrit versus Italian, French, Chinese, Italian, anything. And the fifth would be something passive. So listening to either chant or listening to Chopin. So instead of active, like
Right.
I could be a monk and I just listen to all these songs and chant, but I'm not really paying attention to it.
Exactly.
They're just there as background noise. How does that affect?
Yeah.
And then in terms of the stress, physical stress or modern stress, how does that interact in terms of a presentation if our mic isn't working?
That's right.
Someone has been chanting intentionally versus someone who's been listening to Chopin in the background. How does the two react when that mic doesn't work?
Exactly. They're all really very doable. And any experiment, as Sarah was alluding to, you need a lot of control, a lot of appropriate comparison, so you can subtract away the shared function. But each of those is doable. Go ahead, Sarah. And
I just
somebody
have
was.
one question. Yeah, I'm going to pass it over. But what is the kind of the overall goal? Just want to ask a question more than
Yeah.
contribute. But what were you hoping, as other than just showing impact? You know, you can put on one person, they do something, it changes.
Right.
What do you kind of like? What's the thought you want to contribute to this group's knowledge, to the literature on Sanskrit? Because there's not much. I mean, what was the hope between you two, and also in terms of the mastermind?
Yeah. So Sarah, what I would say is the hope first was to give people familiarity with this, and to show how the technology works, and then as we identify priorities for this group. I would recommend that we actually do a real experiment, which we can't do in the next hour or even in the next day, but we can do with this equipment, and we can do collaboratively. So my idea would be that we should tackle something that has no data, particularly relevant to Sanskrit and questions we care about, or meditation and Sanskrit, questions we care about, and actually do a real study. But a real study is not going to happen in one day. It will get started. And so that's where, but my idea, and I think Shanta's, is to come out of this with a sense of the East-West science and philosophy connection at the ashram, and how we might be able to, as you and I are doing, encourage new kinds of research using these technologies even here. So that, and so anyway. So listen, go
I
ahead.
guess which I should mention that, or we should mention this, that we will not be able to do a real experiment during the next days.
Right.
So what we will show you is how this instrument works, a kind of demo. We could do some things where we could look into functions in the brain in the different areas, but even all these are brilliant questions and brilliant experiments that we could conduct, but we will not be able to conduct today or tomorrow or the day after, right? So I should mention this, that if some of you are hopeful that, okay, tomorrow we're going to see that there is a difference between a meditator and a long-term, that's not going to happen. But what we will see is the way to do that.
But I totally agree, and Nabin, but we have to make that clear. But it is possible for us in today and tomorrow to have something that's kind of brute force.
Yes.
Like chanting versus listening. It would really differ in the brain. You might see signal at the single subject level. It's not clear. But I think we could do that in a sense as an alternative to squeezing and getting motor response. Yes. It would not constitute the final experiment, but it could be a start. Go ahead, Sarah.
And maybe reciting the mantra silently in the brain.
Yeah, of course.
Yes.
Yeah, but then we need, in any science, and this goes to the question you were raising before, we need enough people to go through it so that we can establish statistical relationships with confidence. But this is where it starts. In fact, in my lab, and Nabin and I working together, we spend days just like doing this and arguing and saying, let's do this, that doesn't work, let's do that. So I wanted to give you that sense. We want to demonstrate the technology. Maybe we could do something in the next day, like really what they call brute force or pretty extreme, like chanting versus listening. And we sort of know some of the areas will different, but we will see what maybe people with experience show. Go ahead, Jayshree. Yeah, let's do the demo. Yeah. So we need to get somebody. We need to get somebody to come up, right? Nabin, should we go for it? What do you think?
Yes. I don't know. So I should mention that it's just 13 minutes till 5, and I think that's our time.
No, but they said we would be able to stay until the dinner.
Yeah.
Which
that's
is 5:30. So we have time.
Okay.
Yeah.
So.
RG has been waiting a while.
Oh, sorry, RG.
Sure.
Go ahead.
That's
go ahead.
quite all right.
Please. Sure.
Okay, but we need to do this in parallel, so I think we should try to at least get
what
set
I would
up.
do is...
Before we get to Margie and Rob, let's just get somebody sitting up here.
So I have a capsize.
Yeah, Indira.
Here's an announcement, guys.
Yeah, go ahead.
So the capsize which I have set up, the uptoads, is 52 centimeters, right? So we need a lucky volunteer. I'll measure the head size, and whoever's head fit into this cap can be a volunteer, right? Sorry,
so
but
maybe let Indra, if you want to come up, let's see what your.
Whoever is interested, please raise your hand, and I'll come there and measure your head.
In the meantime, right? Let's go back to the two questions. Go ahead.
Okay, this is not.
That's not necessary.
I did want to remind people that if you're lucky enough to be here Monday, there's a panel. So
Yeah, we're going to. Yeah, and the other thing on Monday is we'll have Nabin here, who is doing science and Naren and music. So,
yes.
But go ahead. Let's Indra, do you want to come up and we'll set you up or measure your head first? Go ahead.
Okay. As a musician, sound healer, meditator, and privileged member of this wonderful ashram family.
Okay, that's not a problem.
One thing that Raji and I have been increasingly asked to do is the laughter release yoga therapeutically. We use the model that Dr. Nabin Kataria began in the 80s. Yes. So not for now, but just to plant a seed, I would love to see what happens when we coach someone through laughter release therapy.
Yeah.
What happens in the brain? Is the cortisol lowered? So thank you. That's
exactly, and that's the thing. Well, go ahead. Let's. What? Okay. Yeah, but Rob, go ahead. Sorry.
I thought it would be interesting to
Wait,
see...
let's, I can't hear you.
I thought it would be interesting to see if there were, what lights up during a nada yoga, during not just internal japa, but unstruck sound entirely, and how that would look different from vibrations going out, these internal vibrations.
What is your prediction?
That
would be a great experiment and doable, by the way.
Yeah, I think there would be activity. It wouldn't be completely silent, but
in the auditory cortex, we kind of know that imagining will create that, but there's something more. Go ahead.
Well, there is a vibration. There's
happening. A vibration. That's right.
Even though it's not, pravriti, it's happening. And then I just had a question about the entrainment experiments.
Yeah.
Does that require that the pairs of people be in the room together, or would a video mediated situation produce the same result?
So, first of all, that's a great question. There is work with babies learning a language that our lab at Haskins has done over the years, and showing that being face-to-face with the teacher has a more profound influence than watching it on video. The big question for entrainment is whether you can entrain to a video. Surprising, well, it's all brand new. Entrainment's just been like a hot topic for the last 5 years, and there's no data yet, but I'm sure people are looking at it. My feeling is that the entrainment is something a bit deeper and probably wouldn't pass through a video system, but it's a question we've often said, we should do this, and we haven't done it yet.
Get Zoom to fund it.
Yeah. So anyway, we're looking for a head, right? He's got not a lot of hair, okay?
Oh, here, check him out. Yeah.
But Nabin, look how great his head is. Hair is a problem with the... Oh, did that work? Yeah, okay, sorry. Do we have anybody?
I think we can fit into a 54, but there are 1, 2, 3, 4... No, wait.
Okay.
54 foreheads, right? So, yeah, so... 454 heads. So we want to do a lucky draw?
How about you, Maya? We have the kids' cap, but they're in the other room. Okay. Well, you have to sign this. You have to sign like that. We're not... No. Oh, well, yes, if you... how about you, Professor? How big is your head? And by the way, we have caps for everybody in the lab, but they take a long time to set up, so we're just trying to shorten this.
Sizes all along,
I know.
Right? It ranges from
we could
28
be here
to
for years
63. So we would fit in everyone, but I only set up one cap for today.
One size is. I hope he works. I liked his chanting this morning. It was great.
Do all of this in frame.
How about you, Shanta?
It's 55. So
close enough? No.
Yeah.
Who do we have?
So we had 454. So whoever wants to come from 154, okay.
Okay.
Do you want the 53?
Okay. So, okay. Now, when we start collecting data, you can actually come up here and see.
Oh yes, please. Have a seat.
No. I'm like, I don't know. Because the machine, the machine that's running this is not hooked up.
We can try to put in the SDMI in the
really?
PC. Yeah.
You could do that?
Yeah.
That's long enough.
Oh.
But we're not using this.
If we want to project the results in real time, we need HDMI.
Damn it.
We need a longer SDMI.
You would have to let me know.
Yeah, that's okay.
Yeah, sorry, no.
We're improvising here. This is like improvisational comedy. Okay?
Yeah, we can move this here.
Then he's going to scream.
Okay. Let us try.
The people can't see me.
I will take this off. This is not needed now. You could leave this in the chair.
Okay. Yeah.
And I think it's not attached.
No, but Seth, I think. So Yeah, I know, but let me just explain. How many people are on right now? Seth? We just need to let the people, for those of you who are live streaming, we are sorry, we have to put the machine in a place where you can't see it, but we are recording this, and also we'll be happy to share any information that you can't see. Stay with us, though. Oh, this is great. Seth, this is worth all your pain. You can actually see. There you go. The Guru's blessing is on us with that.
So I have another idea about what
Yeah,
we
go
could
ahead,
look into
Tracy.
while we're setting up.
Yeah.
Is getting the perspective of somatic movement.
Guys, wait a second.
I hope I won't be discovered.
We will.
Go ahead, Tracy.
Looking into the effect of somatic movement
Sure.
on Sanskrit study and learning and memorization.
Yep.
And which could include chanting while you're writing, or
Right.
speaking it while you're writing.
That's right.
Or some kind of movement to associate with a rhythmical kind of movement and learning and memorizing the words, and just some way to help learning.
Exactly.
In addition to just sitting still all the time, which is what we do a lot of.
That's right.
Also, what would happen with a massage beforehand, or doing
wow.
breathing techniques beforehand, or doing yoga beforehand, and then it's like what we do here. We do
No, exactly.
yoga and
And-
meditation, we chant,
Exactly.
put the whole picture together and see how it all affects.
No, as you can tell, all of these ideas, almost every single one, all of them in principle could be turned into an appropriate design with appropriate controls and enough power.
Is it too tight?
And we could do it.
Yeah.
So,
Deven, go ahead.
No, just the idea being that you mentioned before about different ways in which to do the same verse. So I was thinking one way.
Is it okay or is it too tight? Should I loosen it?
No, it's
metrically chant it and the English translation. There's all these different ways.
That's what I think we should, if we had, if we can set something up, we may or may not for tomorrow, because there was some problem with the repowering. But if we could easily have the experts like you guys just go from simple reading to reading aloud to reading with prosody. And I mean, we kind of know which brain systems are involved, but what is special about Sanskrit? We could do that.
And it is, when I was at Berkeley, the first semester there, the professor didn't chant, but he did Mandakranta meter. And I was the only one in the class who had the right beat on it, because I had it through chanting here. It's the same meter we do, Brahmanandam. It's that meter. But he was wanting us all to say it in class, as Deven was saying, with the right beat, but he didn't add the tune. So his idea of
between the source and the
breaking it out is really cool.
I love it. And in a real experiment, if we did set this up, you would have a condition where there are very similar experiences with one difference. And then you would have expertise as another variable. Somebody who really understands it, somebody who and you could solve the brain puzzle for this. So, what are we going to have her start with the motor thing, or should we have her speak?
I think we could have her speak.
Okay. So, could we do
and
something?
Speak and then chanting, speaking.
Do we have a
just
printout of anything? Oh, I had your. Deven, I got your, I have it, I think. So again, we're improvising people. This could go on for years if people are interested. This is our equipment, we could bring it anytime. So maybe what you could do is start by reading this silently, and we'll tell you how many, what do you think for this?
Few minutes.
Okay. And then, because you do chant, you speak aloud.
Or you could,
it's about glasses.
Oh, glasses!
Oh, but maybe what we could do is there something you could chant without without having to read?
Yes, I think would that be
I think
better?
that would be better. Yeah, I think that would be better.
Chant something without having to read.
Guys, again, this is just a demo, but maybe we turn it into something. Oh, yes, sorry, Seth. Okay, I like to be close to people, that's the problem.
It's much better for the presentation if you're in this area adjacent to
Yeah.
the table.
By the way, I've been chased all over the world by the best of them to get me to
What is your
stand
age?
in one place.
74.
It's never worked.
The last time.
Right, Jayshree? How many times have I gotten yelled at around different places for walking? But it's my fault. I take responsibility. Oh, for God's sake. So what are we going to do then? Huh?
They have the
Okay.
lights on you. It looks nice.
There we
Okay.
go.
So
Above all,
it
science
is
should be
recording
fun.
your brain signals, right? So what do you see
Oh, guys,
there?
this is real data now.
Okay, so I should explain it a bit. What is going on here is, so C has 8 optodes in one hemisphere, and then the other 8 in the other hemisphere, and the blue ones and the red ones, which you can't see it here now, but so there are 4 sources and 4 detectors in each side. If you remember the slide which I showed before, the source sends the light, and then the detector captures that, and we want to see how much signal is attenuated through when passing through the brain tissue, right? And this is exactly now happening in her brain, and this is the live signal that we are seeing there, right? So this is recording her brain in resting state because she's not doing anything now. So what we want to do is let's start her chanting something which she already knows.
Do you want to start with that or not?
We could. I mean,
just for how long do we need to get enough signal?
So if you would move
so
this
first we're going to
hand.
find her motor areas by having her squeeze her
So you could
hand.
see in the signal that how the brain signal changes when she moves her hand, right? Mm-hmm.
And we know where that's coming from, which optode. So we can say, oh, that's coming from the left or the right or the parietal or the temporal lobe.
I'll change that.
Hey, Tara, I thought you were going to... Tomorrow, maybe.
So what happens is that the machine it just adjusts the scale of the y-axis when it sees a signal, so that we know the noise. But if I would reduce the scale, you could clearly see.
And I think you're right, though. Nabin.
Okay.
Maybe we can have her chant. That's great.
Yeah. So this was just a demo to show that actually it works. So if she moves her hands, you could see there's a signal on the last 2 channels, right? So this is her right hemisphere working. And if you put your hand down and if you use this one now.
Now it's going to be the other side.
Where's the other side?
When you start chanting, chant into here.
Okay.
Oh, there we are. It's a weak signal on the contralateral. But it's there.
Yes.
There it is.
So there it is.
Well, we haven't optimized. You have to really do a couple of tests to get optimal signal out of every optode. Yeah. Well,
You can hold them out.
Seth, can I ask you that thing I was going to ask you about these lights?
Yes.
If it's okay,
yes.
yeah.
Yes, but what we would do is, let's say you would just chant without the hand gesture for like maybe 30 seconds or a minute, and then we would do the hand gesture plus chanting.
Okay.
And then the next step after that would be you would chant without, or not vocally, just in your mind. So you could do 3 different conditions, and we could see how the brain signal differs. Okay, so which one do you want to start with?
So I'll chant, then chant with some hand movements, and then chant in just with not
silently,
not audibly chant, just inside.
Okay.
With hand movements or without, like silently but with hand movements.
We could do both.
Okay.
Silently with hand movement, silently without. We could have 4 conditions instead of 3. Okay.
And if we had time, we should get her resting as well.
Yes.
So there'll be a point where she does nothing, and then
So the resting is always important because you would need a baseline to compare. Right. That we know that this is the signal of her brain when she's not doing anything, and then we would compare 4 different conditions. 1, she will be chanting aloud. The other one, chanting aloud with hand movements. 3rd, chanting silently. 4th, chanting silently with hands movement. Okay. So we'll start with chanting aloud without any hand movement.
Om Karagre Vasate Lakshmi Karamule Sarasvati Karamadhye tu Govindaha Prabhate Karadarshanam Karagre Vasate Lakshmi Karamule Sarasvati Karamadhye tu Govindaha Prabhate Karadarshanam.
Very nice. Now these, when she's squeezing her hand, that's a very high signal, but for the chanting, it's in there, it's just not as clear to see.
There's a time delay.
Well, because it takes a few seconds for the blood flow to change, and then we're detecting it.
Yes. If you remember the peak, it takes 4 seconds to get to that peak and 5 seconds down. So it's always a bit delayed before you see the response. But now I reduced the scale so that you could see actually the movement. Because before it was like the scale was pretty low, so you don't actually see anything. So that's why I'm increasing it so that you could.
Oh, there you go. Yeah.
Right.
That's a more fine grain.
So when you see this, it's not as the beautiful pictures what we showed in the presentation. So that means you should. So there's a lot of computation that goes when you capture the raw data like this, and get rid of all the noise, get rid of all the signals, and only take those signals which is out of interest and build those pictures, right? And it's that is a lot of computation. So we will, I think, unfortunately, not be able to see those actual pictures, what I saw in the presentation, but this is the kind of data what we would want to collect. And this is when we collect this is great, and we could do that afterwards.
Can you chant it one more time, because now you have the scale.
Chant it out loud with hands or without hands? Okay. Okay. Hands or no hands?
No hands.
However you want. No hands. Okay.
Karagre vasate Lakshmi Karamule Sarasvati Karamadhye tu Govindaha Prabhate Karadarshanam.
We would need to get these optimized, opt out by a plus, just to make sure we got good signal.
So I guess you saw the difference in the brain signal. When she was chanting, there was a higher frequency waves going on. And when she's silent now, there is much more smoother signals. So there's a lower frequency or the constant frequency going on. It's much more regular now than when she's chanting. And I mean, it could be both things. I mean, she's moving her mouth, and the whole thing is moving. There are a lot of noise included. But there is also a lot of that brain signal that we capture when she's chanting. Okay.
And
What if she speaks it rather than chants?
Sure.
Yeah, that's what we were talking. Yeah.
Yeah,
You could do that, and then you could silently imagine
talking.
Karagre vasate Lakshmi Karamule Sarasvati Karamadhye tu Govinda Prabhate Karadarshanam. Prabhate Karadarshanam.
Okay, so if you would just keep quiet and do not do anything, wander your mind, like what Sarah said before, for a minute or so we could capture the resting state data.
or just watch the breath.
Mhm. Okay, so I guess we can stop the recording. So we have recorded about 10 minutes of the data, and this would be the raw data which we could use to do a lot of different analysis. And so this is just a demo of what we could do. And in a real experiment, it will look slightly bit different. It will be much more constrained in what you want to do, what you should do, and what you shouldn't do. The one interesting part is the sour cap, which I didn't put in. And in the actual experiment, we would actually put in because it would reduce the light noise that's coming in from here, because it's the nanometer lights which we send in, so we don't want that to disrupt. So we would normally put in the sour cap, so that the black sour cap, so that it doesn't hamper. We didn't do it today for the demonstration.
And we also, for each of those optos, those little detectors, we spend a lot of time making sure it's entirely tight and clear, and you get a smoother baseline. But you could see, and certainly if you know what to look for, you could see the increases. And if you did enough of those and you did statistics on that, we can also say where they were found, and then that can be mapped onto the standard brain that you've been looking at.
So I just took out the two optodes to show you how it looks like. So the blue one is the detector, and the red one is the source. And so at the tip of it, you could see the small glass which emits the light, actually. And this is what I put in here and here, and these are just the screws to fix those.
Now I think we can turn on the lights. Thank you.
Okay.
So
it doesn't hurt.
It doesn't hurt?
So
no.
One of the things as we maybe come to the end for this session, we're dealing with a little technical thing that we have to see whether it is. What's the word? Recharging adequately. And if it is, and if anyone's interested, Naren and Deepak offered to let us use the music room tomorrow, and even into Monday, and we can. People want to kind of participate.
Yes.
But the other thing I would recommend is even over the course of the next day, if you have really hard thoughts or important ideas that you think would be worth discussing, we can bring them up on Monday when we have the closeout. What should we be doing? What can't we do with these technologies? We wanted to show you, give you a sense of the science, its sort of utility. But while we're here, we can think about the way we can use it in the context of Sanskrit. And I think whatever we can or can't do this weekend, this is our equipment. So we can do it even at a later date. Yeah, go ahead, Jeshri. Oh, Shanta, you go ahead, Shanta.
Yeah. This on? For those of you who want to carry this on, this was just meant to be building blocks. We're hoping this will continue on for we don't know how long. But we'd like to have more and more of these sessions over time. So all of that, what we're talking about today, is building blocks. And I've got email sheets. If you want to put your name and email down, we'll be sure to keep in touch with you about further development of this. And we're hoping that it will continue on for some time.
Thank you, Shanta. And when we collect the data tomorrow or today evening, if anyone is interested to look into it more, they are more than welcome to come there. Okay, so we will probably we will let you know where we will exactly set it up, and whoever will be interested, just come by and then we will see. 52 to 54, or smaller.
We have the other caps, but Seth is telling me to conclude. Oh, go ahead.
Yes. No, I just wanted to mention that. So we have a other cap, which is even smaller. It's like 48. But so it actually looks like this. So it takes a couple of hours to bring it to this one, right? So you have to do it all with hands. So you have to put in each of these things inside this and then put the fiction. So that's why there's only one cap for now. But in theory, we would have more of them. They do. But I mean, we have more of those in the lab. But I mean,
And then are you able to then go from these lines to like brain mapping when you show those beautiful images?
Of course, because each of those little S8 and all that stuff on the side, those are optodes that are placed at different points on your scalp. So they're looking at what is right underneath them. So if we're seeing things in
screen to like show
then we translate them into those kinds of images that you were looking at.
So it's not an instantaneous thing.
No, there's a lot of
no. So if you want to see, so this is how the model would look like. So this is a 3D brain, and these are the electrode numbers that show us. So what you need to do is you need to exactly know. For example, I know in this cap that number 4 detectors in the right hemisphere goes to FC5. And based on this map, I will exactly know where is FC5 in the brain is. And that's how I map it to the brain. But this is all done post-processing after that.
Looking to see the images of where it was affecting the brain, what she was doing.
Yes.
That's what you're trying to do.
Well, one of the things, Scott, he showed was like when she was squeezing, I think, her left hand, that would be the right motor area, it's contralateral. And
Yes.
you could see that. And then when she squeezed with her right hand, there was a little signal in the left. It wasn't optimal. But that's the kind of thing it's very good at localizing things, and that's how we use it. We're running low, but let's take 2 more. Go ahead.
Were the 2 data sets, the left and the right, the red and the blue line?
No. The red and the blue line are the oxygenated and deoxygenated, right? So
it's literally which areas are increasing the blood oxygen. Essentially the red blood and the blue blood.
So the y-axis was...
And the y-axis was just these different, it's just actually a nominal, it's just the different optodes. But we know if it says this, it was an optode from here or from here. Remember, he said we had 16, 8 on the left and 8 on the right. We can show you. But it's, now with an fMRI, which is what I used, the other research, as Nabin said, you can't bring it to the ashram, you can't do like soccer goals and things, but it has other advantages. We use all of them. One last thing for those of you who are nerds like us, this cap allows us to combine the NIRS, which is the blood flow, with something called EEG, which gives us very precise timing, and we can put them all in the same cap, which is what we're going to be doing for my NIH study with kids. And that gives us really interesting information, not only where things are happening, but when. And that we just didn't set that up for today, but that's what we do. Anyway, I think we need to go to dinner, so let me do 2 things. And Seth has asked me. Number 1, I really want to thank Nabin and Sarah for their incredible contributions. I want to thank Shanta and Indira for having come up with this idea. And on behalf of the Pocket Protector nerds, us, let's just end with Om Shanti. Om Shanti, Shanti, Shanti. Thank you, Seth. You were amazing.